Hello, hello. Good morning, everyone. Everybody is having a nice time, I guess, with these wonderful talks and lectures. And I think everybody had a great dinner yesterday. So, welcome to day 4 of the Young Astronomers meeting. And today we have, in this session, we have around 5 talks. And we first start off with a talk by Professor Maheshwar Gopinathan. So, Professor Gopinathan is an associate professor at the Indian Institute of Astrophysics. His research interests lie in various aspects of molecular clouds, including their formation, evolution, and subsequent star formation, using multi-wavelength and spectropolarimetric observations. Professor Gopinathan has a long association with Aries, as many of you are already aware, and has a major contribution to the setting up and operations of the dot. He was by far one of the most popular scientists at Aries, loved by students and staff. We are grateful to have you accepted our invitation at such a short request. And I would request you now to start with the presentation. Thank you, sir.
Thank you very much for the introduction, and I thank the YAM organizers for giving me this slot to speak about the star formation. YAM is a nostalgic feeling because I myself have organized YAM when I was doing my PhD at IAA. So I think it's a good podium for the people to come together and interact. I think you may not get a chance like this where only students coming together and having a meeting like this. So I guess you all will be like making use of it very well. Okay, so I'll just give an idea of the star formation. Basically the stellar cradles in solar neighborhood. Okay, so it's not very high redshift or something like that. It is within our galaxy. So I think many of you might be knowing Mark Twain. This is his pen name, and he writes. He wrote several novels. And in one of it, in the novel, which is The Adventures of Huckleberry Finns, he said, "I'm loving to live on a raft. We had the sky up there, all sparkled with stars, and we used to lay on our back and look up at them and discuss about whether they were made or only just happened." And his fellow argues that they were made, but he says, no, it cannot happen, because it's so many, so you cannot make it. It just happened to be there. So it's the curiosity of the people when you look up and you see so many stars, so many objects, that you wonder what they are and how they have come there. So this is perhaps one of the most important plot for the stars, where you plot color and luminosity, and you get the domains which are filled up with the positions of the stars. It actually gives you an idea of the stellar evolution, and people knew it. So stellar evolution was quite well understood, mainly from the main sequence to subsequently what happens, whether it ends up in white dwarf, neutron star, black hole. But the evolution from the main sequence was known to all. So basically, you say that, okay, they are there and they evolve, they die. But, do they really to make them? Because from the stellar evolution, that O and B type stars evolve faster. That means if you're looking at a galaxy and if you see a lot of blue sources, that means they are not very old. They have been just recently formed, right? And when people looked at clusters, they see that there are a lot of sources which are in the lower end of the HR diagram, which are above the main sequence, where you should not find them at all. That means these are the sources which have not yet reached main sequence. They have not yet even started hydrogen burning in the center. So they are actually evolving towards main sequence. So now we have sources which are like, many of them which have been identified, which are like, if you put it on a chart diagram, you see that they are, plenty of them are on above the main sequence. So whole idea of star formation is, how do you understand their formation, evolution, and what happens when they reach to the main sequence. So when I say towards the end, it is like closer to the main sequence. They're approaching there. And that's where our interest lies, because that's where the planets form, right? So that is where we are more interested in. But what we know is there is molecular cloud and there are stars. What is happening in between is what we need to probe. Even here, when we say that there is a cloud, but you don't know from where these clouds are formed, obviously from interstellar medium, but in most of the theoretical understanding of star formation, that part is very weak. We just take it for granted. But we need to understand that as well. So you need to make these clouds from interstellar medium, and then you make stars inside those molecular clouds to basically get what is the end product, which is the stars. There are 4 hurdles for making stars. One is the pressure hurdle, because when you have a gas of a blob of gas given, and you need to now, that will be so you have to basically collapse to form the star. And the collapse cannot happen because the pressure in the gas is opposing the gravity. So that can happen only if there is a critical, the mass reached by the cloud for it to collapse. Basically, gravity takes over, and nothing can support it. So this pressure hurdle has to be overcome. Then there is something called dynamical hurdle. That is, a cloud collapses, but it cannot keep on collapsing because the gravitational, energy has to be taken out. So otherwise, it will cease to collapse at some point of time. So that is another. Then the angular momentum hurdle. So your cloud is so big, and you are making a star out of it. Single, right? When it's stretched out, and when it is done closer to your body, the angular momentum goes up. So basically, you are now from a bigger scale. So that has to be taken. Then there is something called magnetic flux hurdle, because of the ionization of the interstellar medium, these magnetic fields are frozen in the gas. So if you are bringing them together, that means you are increasing the flux. So that magnetic pressure is going to oppose the gravitational collapse. So that also has to be. So if nature wants to make molecular cloud, it has to overcome these 4 hurdles. But we know that there are stars. There must be, nature is doing something to basically overcome this hurdle and making the stars. So whole understanding of star formation is to understand basically, how these hurdles are being overcome by the nature and how star formation actually happens. So star formation is by far one of the most fundamental processes, basically because if you want to understand the galaxy evolution, you need to understand what is the process that are involved in star. Be it the galaxies which are very close to you, or be it the early galaxies that JWST is going to find out for us. So you need to understand what is the star formation, star formation processes involved. Now we know that Milky Way contains about 10⁻11 stars, and they are at different ages. They are at different evolutionary stages. So it is a formation happens, whether it is predominant towards the center, if it is outward, how that is going. which are basically the regions which are predominant in O and B type stars. Now, star formation occurs in molecular clouds. Now we know that. Okay, so these are the sites of star formation. And the total mass of the molecular portion in the Milky Way is about 10⁹ solar mass. This is understood from the CO surveys because you cannot use the most predominant, the molecule in these molecular clouds, that is H2, because of the obvious reasons. So what you do is you look at the next most abundant molecule in these regions, basically the carbon monoxide, and then you calculate what is the total mass in the star formation occurs towards the center, as I said, and also towards the outer regions. So why that is happening? Is there a propagation of star formation? Is it that the spiral structure that we see has anything to do with the star formation? Is it that something is increasing the density over there, which allows these regions to form the stars? Star formation can be isolated. It can be in clustered mode. I think Aries has a good number of people who works on the cluster mode of star formation, but there are regions where star formation is isolated. So why is it that some of the regions are forming stars in isolation? Some of them are in a clustered mode of star formation. Why is that some region is forming massive stars? Why some regions are predominant in making low mass sources? These are some of the examples of the single isolated mode of star formation, where you have a cloud and a single star is forming. Whereas this is an example of a region where you have cluster mode of star formation. So you need to go and understand what are the physical parameters that are existing in these regions to understand why these regions are differ in the mode of star formation. Now, this is one of the classical, the example of understanding what a molecular cloud is. So if you look at a molecular cloud in say blue wavelength, you see it as a dark hole, right? So sorry. As a hole in the sky. In fact, initially people thought that these are indeed holes in the sky. Then when you look at it in the longer wavelength, for example, micron, you see that the cloud is almost invisible. That means the material which is there inside this cloud is not affected by the radiation that is coming from the background stars. So these are all the background stars that you see. So the particles which are obscuring the light that is coming from background is actually of the size of or lower than the wavelengths that we are probing in the longer wavelength. So these are basically the solid particles or what you call the dust grains. Now, if you look at, so this is an absorption. That means the material is absorbing the light that is coming from behind. But if you look at them in thermal radiation, the very dust particles which are absorbing the radiation is actually emitting the radiation in the longer wavelength. So if you can get what is the sense of absorption in these particles or what is the sense of emission in these particles, you can actually calculate many of the parameters. For example, the size, the mass, all these parameters can be estimated. The temperature. Now, if you look at it in the gas emission, they emit, quite strongly. That means they have not only the dust particles, but they have gas as well. Now, we know that the molecular clouds are basically, either they are having the dust or the gas. So if you look at them, you may make a map of the entire galaxy or what is in our neighborhood. You can see there are several star forming regions. For example, this is the galactic plane, and this is the Orion star forming region, which is at about 400 parsec, and it is making stars which are predominantly massive. Whereas if you look at the Taurus star forming region, which is nearby, it's only about 200 parsec, and you see that they are predominantly forming isolated stars over the entire cloud. So this image was made by the Planck, satellite. Now these clouds come in different forms. For example, you can have a big complex, then you can have something called cometric globules, which are basically affected by some sources, some massive source in its vicinity, which is making its unique shape. They can be, like bright rim clouds. You have a very bright rim of the clouds, and this is also pointing towards O-type star, whereas this cometric globule is not. This is the insulated, it's a different kind of source. And you can see this Eagle nebulae, pillars of creation. Basically, they are also pointing towards, one of the or complexes, O-type complexes. So the radiation that is coming from those are actually having an impact on these clouds. And then you see some of the, like Bernard 68, which are like isolated clouds, and they are not getting affected by anything around. Now, if you want to find what is, so this is basically a modern image of an object which was observed by Bart Bok. He did this observation on a Valentine's Day, and he found that there is a outflow that is coming out. So we usually busy with many other things, but the astronomers generally are maybe we are so boring that you don't have anything else to do but go and take images of molecular clouds. So what he found is there is a beautiful outflow that is coming out, showing that these sources are very active and they are actually, the low mass star formation in formation. So this was the first, the idea that these are not holes in the sky, but they are actually regions where stars are getting made. So if you want to find out what is their galactic location, the linear sizes, the linear size of the outflow that you see, the physical size of any filament, or the luminosity of the stars that are formed inside, then you need to find what is the distance. But there is a problem. The problem is clouds have no standard candle. So unless the supernovae type 1 or the Cepheid, you don't know what is there any particular luminosity for these clouds. So you don't know how to get distance to these clouds unless you have a star that is forming there. So you get the distance to that star, and then you say that okay, there is a reflection velocity associated with it. So if star is of this distance, then you can get the distance to the cloud. But if the cloud is an isolated one, there's no star formation happening, there's no way you can find distance to the cloud. So this was one of the problems that was there when I was doing my PhD, and we were trying to find out various ways in which we could get the distance to the cloud. One way of doing it is obviously proper motion. So you might have guessed it that with the Gaia, we could do it, but not directly, indirect method. So you can use VLBI and get the proper motions or the movement of these young stars, and then get their parallaxes and get the distance. But with Gaia, it's just much more. So you all know this, that if you this is basically the distance equation, where you know that if you have a apparent magnitude and if you know what is the absolute magnitude of the star, then you can find the distance, a extinction as well in that wavelength. The problem is finding the extinction and finding the m lambda. You have to do spectroscopy of a large number of sources, which is not really time consuming, but it is it takes a lot of telescope time. So what you have to do is you have to basically find ways, innovative ways in which you can estimate the extinction as well as the absolute magnitude of the star. So if you have a cloud in your field of view, and you can say that there are stars which are, so you will see stars like this, right? on the cloud, there are many stars. And if the stars are foreground, then their extinction has to be very, very less. But if you look at the sources which are behind, they will have high extinction. It's not only true with the extinction, but it can be with the polarization. So anything which is added by the cloud on top of the stellar properties, you can use that to find the distance to the cloud. So basically, the distance will be the place where you see. Now the problem is to get the extinction, because again you need to do the spectroscopy of the sources. So this is basic. For example, is a this is the gas absorption. So if there is a cloud, and if you look at the spectrum of the stars, there will be absorption lines because of the gas present in the cloud. And if you look at these gases for many sources, you can find the distance to the cloud. So if they have a different, the radial velocity. Radial velocity is basically how they are moving along the line of sight. Then their lines will get shifted. So you will know how many components or how many such clouds are there in the line of sight as well. Again, it's time consuming. Polarization. So you can use polarization. So if the dust grains are not spherical, which they are not, and if they are elongated, then an unpolarized light that is coming from a background star will get extincted because of the a process called dichroism. That means one of the component will be absorbed because it is seeing a larger material in front of it. So what you get is a polarization down and a polarization high, and the dust grains get aligned with their minor axis parallel to the magnetic field. The process, which is still not very much understood, but it is taken that it is aligned with its minor axis parallel to the magnetic field. That means that the polarization value that you're getting is actually giving you a sense of magnetic field itself. So this is a way in which you can map the magnetic field in the interstellar medium. And that also, if there is a cloud, then cloud can give you high polarization for the sources which are lying behind, and you can use the same method, like it gives you can basically you can basically bracket the presence of the cloud by using these methods. This was another way of doing it. For example, use color. Basically what I'm showing is to tackle a problem, you come up with various ways. Okay, it's not that you just go and attack it with one way, but you get clever ways of finding the extinction, which is one of the most difficult parameter to estimate. For example, in a color diagram, normally you should see stars in this loci, but what you see is they are distributed like this. So you bring them down and put it on the main sequence and see how much you have to move. What is the kind of extinction you have to add basically to get them bring here, and that will give you the AV, right? And then you can find the distance to it. So you see there are so uncertainties because of the uncertainties in the error measurement, uncertainty in the measurement, and also the stars that you are dealing with. Why there is a cut here? Because this is the loci where M dwarfs are. So if a star is lying here, you don't know whether it is the M dwarf that has gone here or it is actually the G type has gone there. So there is a degeneracy. You cannot do anything with that. Now you know about the pan-star surveys, right? So this is the advantage of having such surveys done, because many people can come up with the ideas that you have because you have the data lying there, and you can use it to whatever ideas you want to implement, basically. So if you look at the different filters, basically G and R filter, this is in the blue part and the red part, and the red part and the beyond red part, basically R and I. You see that the loci of the stars will lie like this. So A, F, G, and K, right? But then the extinction vector is like this. That means if you put a cloud, they will all get extincted like this. So again, you don't know whether it is unextincted stars or extincted stars. So nature's way of blocking you from understanding its secrets. But then if you look at a full G minus R minus I color diagram, what you see is that the M dwarfs are lying here. So these guys will go straight, but M types will go like this. So you know for sure that these are M dwarfs, right? So now the only thing that you have to do is go and find out precisely what is the colors of these M dwarfs, which again you can do by doing, spectroscopy of many of the known M dwarfs. For example, Lamost has done a lot of surveys in M dwarfs, right? So use this data and you can actually find what are the colors. Now you observe a cloud and find out what is the, so this is basically the reason why you get M dwarfs away from the normal color that you see. So you see the M dwarfs, the late type M dwarfs have higher, they are brighter as you go to longer wavelengths. So that is the reason why they go away. Okay. So you make the colors basically, and then you do, take the pan-star data. This is what you get. Much cleaner, basically. You bring them back. Now there was a problem in this prior to Gaia. So you get extinction now, right? But still you don't know what is the distance to these sources. And Gaia is providing you. So you have the extinction from these plots, you have distance from Gaia, you can find distance much precise. So now, after I think 20 years, when I started my PhD, now you have a method by which you can actually get the distance to these clouds much precisely, and which in turn will give you the parameters which are important for the theoretical understanding of the cloud. Now the Herschel has done observations of many of these star forming regions, and Herschel has a much better resolution. So now what has happened is, what people are now seeing is that the star forming regions are filamentary, and this is what you see in the structure formation also, right? Most of the regions are filamentary in nature. So you can see that the stars have a lot of filamentary structures, and these filaments are omnipresent. They are present everywhere. You look at star forming clouds, you look at even non-star forming clouds, you see these filaments. Now the identification of these filaments in non-star forming region gives you an idea that filaments are not formed in the later stages of their evolution, but they are formed right at the stage where they were started forming itself. So any star formation theory that has to explain this star forming process has to take this input into account. And now these main sequences are found to be surrounded by these filaments, right? So what are these filaments? Why are they there? Are these filaments like the feeding channels for the material onto the filament? Do they play an important role in the formation of these filaments? If so, what are other parameters which are, involved in their formation? Now we know that a cloud can collapse if the mass is greater than the gene's mass. And that depends on the two factors, temperature and the density. Now and once it starts to collapse, the time scale that is involved is given by this, the free fall time scale. So now if you put all the masses that we know in our galaxy, and you know the time scale of formation, there's a problem. The star formation rate that you should see in our galaxies is about 300 solar mass per year. But what you see is basically 2 orders of magnitude less. So it's not that gravity is just collapsing all the molecular clouds that is present in our galaxy and then forming stars, but you need something to counter galaxy. And the two of the agents that are invoked for countering these are basically the turbulence and magnetic field. The rotation was initially thought, but it's not that high to have an impact. It could have, but not that much. So the basically magnetic field and turbulence. And turbulence we know is present because of the non-thermal line width that you see towards these clouds. So you look at the CO line widths, they are basically, more than what you should expect from the thermal broadenings. And of course, the magnetic field. So magnetic fields, it all started when people wanted to see what is the expected measurement of magnetic field from the stars. So if stars have rotation, then their equatorial region can have bulge. So if there is any asymmetry in the geometry of anything, you should see polarization from. So people wanted to measure the polarization from these sources, and what they found was that the polarization is very high. Okay, it's 2 to 3% in most of the cases. And that is not limited to one source. You look at the sources around the region, you see polarization is high. That means it's not intrinsic to the sources, but it's something to do with the regions which are between you and the star. So now we know that these are basically from the interstellar medium. And if you look at the polarization map of the Milky Way, you see that the sources which are showing high polarization, that means higher magnetic field, or what do you say, high efficiency of the alignment of these dust lanes, then you see that they are parallel to the galactic plane. So mostly magnetic fields are parallel. From the thermal radiations in the Planck, people have made magnetic field geometries in our galaxy, and you see that they are parallel in general towards the Milky Way, but there are structures as well. Right now, the very fact that you see these, we are happy because magnetic field is there in ISM, and they are contributing to the star formation in some way or other. But I think the cosmology people will be very unhappy because the Planck data is being swamped by the signal that we are interested in. So now you see if you look at the clouds which I showed you earlier, the magnetic fields, how they are aligned. They are mostly aligned perpendicular to the filament that you see. So that means that the striations that you saw earlier is like, is channeling the material and helping it to fall onto the filaments and allowing it to form the filaments. Now, how star formation happens towards the center is something like, this is one of the way nature is like somehow removing the magnetic flux problem. This is basically, you have, if you know that there is a cloud, I think I have, yeah, if you have a spherical cloud and if there is magnetic field in it, now the material can flow along the magnetic field lines more freely because of the less resistance. So you expect something like a disc-like or flattened structure. That's what you're seeing basically. The filaments that you're seeing is perpendicular to the magnetic field, but as these neutrals can flow freely, right? But the ions cannot. So when the neutrals flow, they take the ions along with it, and the ions are coupled to magnetic field. So the magnetic field is also, pulled inward, but the neutrals, because they are more, they can come in much faster, right? So they get accumulated towards the center, and as a result, the magnetic field just diffuses out. So you can see that the nature has a way of removing the magnetic field towards the center and reduce the magnetic pressure for allowing the cloud to collapse and form. So this is basically the called the hourglass morphology. So this has been observed. So you can see that now the striations that you see in most of these are basically these are parallel to the magnetic field, and these are basically guiding the material to flow towards the filaments and form these filaments there. Okay, so this is the Taurus molecular cloud, and if you look at the young sources that are associated on it, then they are like they are like, they are, if you look at the young sources, so these green dots are basically the young sources, and they are predominantly located towards the regions which are, having high density parts. And now you look at one of the regions, this is using Planck. So you see that they are like, diffuse emission. You look at Herschel, you can see that there are sources forming, and you can now start seeing the structures. This is in optical, the same thing that you see in absorption. And if you look at in say mid-infrared, you see young sources forming inside very clearly. So this is basically, multi-wavelength understanding of the regions, basically to understand what is the structure and as well as the young sources located inside. So if you say that cores that do not contain a stellar object are referred to as starless. And there are something called pre-stellar cores also. So pre-stellar core is where the collapse of the interior is not started. And starless cores can be evolved also. That means they have started the collapse, but they have not yet started the formation of the star inside. So this is how you understand the stars. For example, if you have a pre-stellar core, the emission will be predominantly towards the longer wavelength, right? Sub-millimeter. So you have to basically observe in sub-millimeter and identify the sources there. Then you will start seeing a source that is start to see the collapse. And when the initial collapse happens, there will be a disk formation and the material will be channeled towards the center through the disk. At the same time, you see an outflow that is emerging from the sources, basically maybe to remove the angular momentum, and then you find a disk. So if you observe in multi-wavelength, you see initially that the increase is much more, that is the peak is towards the far infrared, but slowly that peak will go towards the black body of the source itself, because now you start seeing the source. And how do you say that a region is collapsing? So this is one of the cloud which was initially thought that it is a starless core, nothing is happening inside. But when Spitzer looked at it, this was the first source that they looked at in the list that they had, and they found that there is a source inside. Now that's basically because the sensitivity of the earlier missions were not enough to pick the source that is forming inside. These are called the bellows, very low luminosity objects. In fact, the luminosity is so small that the mass that you estimate from these are like, substellar. That means they are not stars at all. Maybe this is the way a brown dwarf is formed inside the cloud. Okay, because the luminosity is very low. Or there is something called, the episodic accretion. That is, star won't accrete the matter every time. You just accumulate the matter on the disk, and some points just accretes. So most of the time it will be dormant. So luminosity that you see is indeed much, much lesser. Now, how do you say that a cloud is collapsing? If you look at in the CO, you see a double peak emission. And this actually tells if the asymmetry is shifted towards the blue, then you say that the cloud is collapsing. So you have to observe many of these sources to understand if they are collapsing or not. So the best thing to do is to do a survey of all the regions spectroscopically, and then find out which of the regions are showing this blue asymmetry to understand where these, the collapse regions are in the ISM. And finally, you see, the emission from the YSOs, basically. This is a cartoon of what we understand about YSOs. Now, there is a disk which gets the material, and because of there is magnetic field, this is for the low mass stars. The magnetic field, channels the material and makes it fall onto the source. And as it hits the surface, it emits X-rays and UVs, and you have the near infrared emission from the disk, and far infrared emission from the cooler disk, which is much extended. So if you put them in, the color diagram towards the infrared part, by looking at their locations, you can actually identify what type of stars are these. Whether they have thick disk, whether they have thin disk, and the thin disks are the sources which are interest to you because that's where the planet formation. So it's like it is shedding the disk now, and there may be planets forming inside. And this is basically the evolution theory of these young stellar objects. So these are like the evolutionary tracks. So basically, initially they are convective, but slowly as the mass increases, they become more and more radiative. And at some point of time, you will get only radiative envelope, not the the convective. So the theories have to be, you have to come up basically understand what how to explain the sources that you see by observation. And there is something called observational birth line. Now, birth line is when you see the photosphere of the source. To put it on the HR diagram, you need TFFT, right? So you can get that only after a certain evolutionary period. That is why it is called birth line. And the interesting thing is that if you look at the main, if you look at the massive sources, the birth line goes and joins with the main sequence. That means for the massive sources, the moment you see them, they are already on the main sequence. The pre-main sequence of these sources are you cannot observe because the evolution is faster. So the ones which you have, like this convective things, you say low mass stars or T Tauris. The ones with radiative, you say intermediate or Herbig ABs, and the ones which are like onto the main sequence, you see that they are the massive sources. Okay. So there are a number of regions identified as star formings around the solar neighborhood. And if you look at in multi-wavelength, you see the magnetic fields at different regions, because optical, the extinction, if it is high, you won't be able to see the background sources. So you have to see it in infrared, and emission will give you, towards the center, because the extinction is so high that you cannot use the background star. So you have to use, the combination of all these things to get the magnetic field information from, the outer regions to the inner parts of the Earth. And that's what we did with some of the the instruments by which you can do polarimetry. And this is the aim pole that is there here in Nainital. So we used basically very simple regions, like no complications. For example, this is a much bigger cloud, and we have taken a small region where there is a single filament forming a young source, showing outflow. Now the idea was what is the magnetic field orientation and how it is related to the magnetic field, to the outflow that is coming, and to the single cell filament that we found in this. This was done using the instrument that we had. Now this is basically a low mass star forming, but then the outflows can modify the environment of the young source, and the interpretation of the magnetic fields can be wrong. So what we did is we looked at sources where these young vellows are forming, very low luminosity sources that are identified by Spitzer, basically minimizing the effect of the outflow, because outflow energetics are simpler. So this will give you an idea of whether the outflow is actually what you call affecting the interpretation of the magnetic field from these sources. This is what we did for, this is from the optical, much wider, and then went on to make magnetic field maps using ALMA. So basically from a higher scale to a lower scale to see what is the relationship between magnetic field in the outer regions and the inner regions. This is how star formation happens in the hub filament structures. So basically this was one of the things which my recent students did. This is on a hub filament cloud, and you can see there is a long filament and a hub where massive star formation is happening. And this is about 300 sources for which polarization was done. This was done again using the impole that is here. So I'll just go faster. So this is the cloud. Let's go and show the, yeah, so these two were the students who actually did. So I divided this problem into two. The one person will be working on the young sources that are towards this region, and Ekta was basically looking at the gas dynamics of this cloud. And we used several instruments. So basically, just come. So we estimated the distance towards this region and identified several YSOs. And we looked at not only the cloud, we looked at a big picture, basically. What is happening as a region around this region. And you can see there are many sources. And even we identified a cluster which is very closer to this cloud. This is the one which I was talking about. We identified a cluster here. And this is the magnetic field as a whole. So what I'm saying is it's not only enough to look at one small region, but you can actually connect it with a big picture. So whenever you pick a problem, always take it that you should be able to find a big picture at the end of your work, where this is going to lead and where it is going to give a fit in a big picture of the problems that you are looking at. This is the young sources that they found, and this is basically the gas information. So now you have handle on how the dynamics of this gas is happening around the massive sources. I'm just saying what are the work that they did. Once you know the kinematics information, you can now know what is the kind of effects that are having basically the massive star is having onto the circumstellar material and how it is affecting it. Okay, so this is the magnetic field, the gas dynamics, and the filaments together. So now you know what is the structures, different structures that are forming there, and how it is related to the magnetic field. Okay, this is another important result is that normally people find filaments to be parallel to the magnetic field if there is a hub located. Normally you see it as perpendicular, right? But there are regions where it can be parallel, and wherever there is parallel, the star formation efficiency is found to be much higher. That means the magnetic field is allowing the material to go towards the hub and making a higher mass source there. This is something which we did, I think, the three slides. So you might have seen these pillars, right? Where you have a stone on top of these pillars. So basically, when rain comes down, the stone is actually, hiding this pillar behind. So these are basically the natural way of creating pillars. So likewise, you have these pillars that you see in the H2 regions. So ionizing radiation is basically carving out these filaments in the interstellar medium, and you have this head which is very, high density. So that head is basically hiding the material behind, and you get these filaments. There is something called a rocket effect. That is, when the radiation falls onto it, the gas escapes. Okay, and because there is a difference in the pressure, this gas escapes and goes towards the H2 region. Now, to conserve the momentum, this cloud has to go backward. So it is like a rocket with you are firing, right? Now, this was theoretically shown that yes, rocket effect can be, it's very elegant calculation, but it's very hard to show because you don't have any handle on the movement of the cloud. What you can get is only the radial velocity. You cannot get the proper motion. So what we did is we used all the sources which are present on the cloud, and we showed that, the proper motion of these YSOs indeed show that the sources are going away. And these are sources which are formed inside the cloud. So if the cloud is moving, and the sources which are formed inside, they are also moving, that actually validates the, So the bottom line is that, the takeaway message that I want to give is, when you take a problem, you take it to prove something, it has to be as simple as possible. And, you have to look for such, issues that are there in the broader region. And then you see how you can solve it with, the simple techniques that you have in your armory. And of course, these were the real people who did all the work. Archana, Neha, Ekta, and Piali with me. But I think in Aries there are many who are working now. And it's a bit unfortunate that of the 18 posters that are outside, only one with star formation. I think, yeah, so you can take it. Thank you.
Thank you, sir. Thank you, sir. That was a wonderful talk. I enjoyed it. Questions? One question there.
So my question is, are there any specific distribution in stars in galaxies, or it's random?
Okay, so if you look at the galaxies, the molecular clouds basically are distributed in the spiral arms. And these are basically the density enhanced regions, right? So it's quite obvious that you should see the stars over there as well. If you look at the picture of a galaxy, for example, use UVIT and take an image of a galaxy, you see all these O-type stars, the bluer ones, predominantly on the spiral structures. So yes, there is a distribution, preferred distribution, and you see it mostly along the spiral arms. This is for the spiral galaxy. Okay, but there are other regions as well. For example, jellyfish galaxies and things like that, where you have distribution in a different ways because of some reasons.
Similar question. So the shapes of these clouds, so are these random? Like it should be like some symmetry kind of thing if these are like self-gravitating or something.
Okay, so that's a good question actually. So you won't see a roundish cloud. The most roundish that I can find is that Bernard 68, which is like kidney shaped cloud. So its shape itself is kidney. Normally, yes, you expect it to be round, and that is what you idealize when you do theories and simulations. But in reality, I have not found. So there is something going on. Maybe the radiation from the galactic plane that is affecting, or the radiation from around. So that is something which we also looked at actually. So I didn't find anything which is like perfect. Yeah.
Any more questions? Yes.
So we are in stars, so we have a molecular cloud and there are some background clouds. So in the molecular cloud itself, we will have some ISOs, those will look like redder, and those background star will also get redder. So if we don't have any distance information, then is there a way to distinguish in between these two?
Yeah. So the ones which are YSOs, they will have disk around them. So if you look at them in, say, near infrared, their color will be different. Okay, they will have excess basically. So if you look at H and K colors, for example, they will have emission in that region. But if you look at the main sequence sources, which are basically the background ones, they will have a different loci. So by looking at the loci of these distributions, you can identify which ones are young sources and which ones. And then you can do spectroscopy and get the emissions.
More questions?
For isolating them in a star or cluster transformation, does it depend on the density of the gas cloud or the other parameters?
Oh, that's a good question. Yes, it will depend on the density as well. But more than that, I would say it is the turbulence spectrum that you see in these clouds may be playing a role. Of course, it is the high mass which form the cluster, and the single mode is basically tens of solar masses or even smaller. So these are like small clouds if you look at the efficiency, which is about 1 or 2%, that is given a cloud, what is the mass that you end up with? There is efficiency dependence. So it really depends on the density there. If you have a bigger cloud, you will form more. There's something called initial mass function, which I didn't tell here. So that will give you an idea of what is the number of sources that nature is forming in different mass bins, and that will tell you what is the kind of formation process that is going on. Maybe fragmentation could be one reason.
I, so you're saying you're having trouble before like Gaia to estimate this thing. But like wasn't the workers and typo data they all plan.
Yes, that is. So what happens is Hipparchus has had a sensitivity limit. So you cannot have many sources with distance information. For example, you take a region. Now you search with Hipparchus and you search with Gaia. Gaia goes to about 20 magnitude, right? So your number of sources are going up. And you can see that the place where you see a jump is a statistical thing, right? So you need more numbers to get better results. Yeah.
Yes, more questions? Anybody?
So we are talking about the turbulence in these clouds. So what is the origin of this turbulence? It is the kinetic driven turbulence or somehow magnetic field also plays a role?
Okay, that's very good question to ask actually. So what I didn't talk about is that when I said initial mass function, it is important not only for star formation, but it's important for the people who study the supernovae and many other things, because at the end of the day you need to know how many supernovae form, right? And the energy injection actually to the ISM comes from these high energetic the agents. So if you know the supernovae, the number of supernovae that happen in our galaxy, if I just take only our galaxy, you take those explosions, give it over the time, what is the kind of the number of explosions that are happening in the galaxy, that is the injection of energy going into the ISM. And that will now cascade down, okay, because of the spectrum. Injection is at very high scale from the supernovae, but the dissipation of that energy is actually taking place in these molecular clouds because of the viscosity. So the turbulence nature may be, it depends on, yes, depends on.
Like if we look at so, so let's say if we look at the different sides of this star formation, so we have like majorly two different models. So one is collect and collection, and there is the shock driven model. So like we expect the shock driven model is somehow this shock wave compresses that medium. So do we find the higher turbulent region there on that shock driven side?
Okay, we have not seen. So that's what the the 9 observations will tell you, whether they are really have a higher line width. That is something which we have not seen. But yes, if you look at the sources which are lying around the H2 region, maybe that there may be higher turbulence in those clouds. Yeah.
So I'll take the final question.
Yeah.
So you were talking about the polarization observations, right? You also said there is also gas there. Is it in the plasma form, or do you observe Faraday rotation or?
Oh no, so the Faraday rotation is basically used to get the general ISM magnetic field. For example, the pulsar signals that you get. But for these regions, these are molecular clouds. So you have to use the dust basically to get the magnetic field orientations. But yes, for the low density regions, Faraday rotation can be used to get the,
and are there any
line of
transitions?
sight magnetic field. Yeah.
Now, are there any transitions? So you were showing a couple of spectral lines. Are there any line transitions which are induced by magnetic field?
Yes, so Zeeman effect can be used, but then for that you need high densities, and the magnetic field strength has to be high. So we don't have such high sensitive instruments to basically get the Zeeman. So if you combine these two, that is the polarization and the Zeeman, what you're getting is the 3D magnetic field. So something which, maybe future telescopes can give you information.
Wonderful.
Yeah.
Thank you very much, sir. A huge round of applause.
Thank you.
We have a small present for you.
Oh. Okay, thank you. I appreciate it.
Thank you very much.
Yes.
Picture. हाँ, yes.
ये सीधा करके करो।
सीधा पकड़ेंगे.
Just for the correction, कभी भी दो।
हाँ, ठीक है.
Thank you.
Thank you very much. Yes, so after that excellent talk, we now start our contributed talks. And the first contributed talk is by Somiranjan Kuntia. And he shall talk to us about evolution of internal thermodynamic state of coronal mass ejections. Somiranjan, you have around 12 minutes for talk. 10 minutes Q&A. Okay, I'll tell you at 10 minutes.
Vaccine. I am audible. Okay, so I am Somiranjan Kundia, third year PhD student from IIA, Bangalore. So I am working with Dr. Vagesh Mishra. So today I'll present about the evolution of thermodynamical state of coronal mass ejection. So this is the brief outline of my talk. So the CME, then motivation, then the model I have used, then result and conclusion. So yeah, sorry for the GIF. So coronal mass ejections, these are like large magnetized plasma that erupt from the solar corona into the heliosphere. So they are discovered in way before like 1970 in OSO 7 spacecraft. So we can see those faint structures like in the solar atmosphere just because of this coronagraph. So this coronagraph occult the solar disk so that we can see the faint corona around the solar atmosphere. So when a CME eject, it has obviously the density higher than the solar atmosphere. So we can see just because of the Thomson scattering of the photospheric light by those the ions and the electrons present in the CMEs. And if those CMEs like travel in the interplanetary space, those are termed as interplanetary CME or ICMEs. So the CME structure can be vary. So, but in general, they are treated as a three-part structures. The first one is the bright leading edge, this one, then followed by a dark cavity, then a bright core. So, what is the importance of CME? So, CME they can affect the space weather. So, space weather means the changing atmosphere around the sun or the interplanetary space or in our planetary atmosphere. So they can generate like intense geomagnetic storm in Earth, and then also they can put some problem like they can increase the atmospheric drag in the upper atmosphere. Also they can disrupt the satellite electronics and GPS signal, etc. So these are some recent news you may heard that 40 Starlink satellite get doomed due to the geomagnetic storm that happening that time. Also, this is a great event like the Carrington event in 1859. So this is the largest geomagnetic storm ever recorded, and people found out like if the same event occur in the 21st century, it can cost the damage cost can be around some trillions of US dollar. So this is the practical importance is our one of the motivation for my work. And another motivation, like the CMEs are discovered like way before 1970, but after like 5 decades of work, we still have some uncertainty in the prediction of the arrival time at Earth. So this is because like the physical mechanism that launch and drive the CME is not fully understood. And in the theoretical model, like in the MST model, we put some other assumptions in the internal properties of CME, so that like put some uncertainty in the prediction. And also the CME propagate in the interplanetary space. Also, it expand in the as well as the propagation. So the reason for the forces for the expansion of CME is still not known yet. And another parameter is the thermodynamical parameters. So the internal plasma parameter, like the temperature or the pressure, these things are not understood fully, like the evolution is not understood. This is because like to know the thermal parameters, we need spectroscopy, and spectroscopies are done at simply near the sun or somewhere in between, but we don't know like the whole profile from sun to Earth. And only observation that can be done, like it's the white light observation that can be done from sun to Earth, but the white light observation we don't get the idea of the temperature something. So it can give some density profile of the CME. So also another problem is like when CME launches from the sun, it has some temperature about 10 to the power 6 to 10 to the power 7 Kelvin, but when it reaches Earth by the in situ measurements, we find out like the temperature should be like we can expect it should be something 10 to the power 3 to 10 to the power 4 Kelvin, just if it is like expand in the adiabatic manner. But what we found like something around 10 to the power 5 to 10 to the power 6 Kelvin. That means in between the interplanetary space, the CME somehow get heated or it maintains its temperature. So we want to know like what is going on in the interplanetary space. So that leads to our like the so to solve these two big problems, we take a baby step like to know the internal plasma parameters and to know the internal forces for the expansion of the CME. And also, as I said before, like we know some parameter near to the sun, we know some parameter near to the Earth, but we don't know the total evolution. So we need, so we try to bridge the gap between that one solar AD and one AE. So that to measure the internal plasma parameter, we have used a model, the Fluxdorf internal state model or the freeze model. So this is like a typical local scale as a cylindrical shape as like R5Z coordinate, and this is expansion colloidal speed, and this is the propagation speed of the CME axis, and this is side view. So we consider the CME the CME to be axisymmetrical cylindrical Fluxdorf. That means that around the axis all the properties are the same. Then the self-similar expansion, that means the radius of the Fluxdorf as it expands. So we somehow like to connect the radius of the Fluxdorf and the distance of the axis of the Fluxdorf to the like solar surface. So the self-similar expansion that describes that, and as the CME is a plasma, it contains plasma, so we treat the plasma to be quasi-neutrality, and viscous force and gravitational force are ignored in my derivation, like the derivation of the model. So just this is the flow of the model, like treat the conservation of mass and angular momentum, simple magnetic hydrodynamic equations, and we put some laws of thermodynamics in between that. Also, we treat the CME when it evolve during the interplanetary space, it will go through the polytrophic process, and then we derive the radial equation of motion for the expansion of the CME, and then some additional constant to find out the thermal parameters. So this is like the initial state, like this is the simple MSD equation. Sorry, this is to convert in the some PPT form is changed somewhere. And this is the radial part of the equation. So after doing all those exercises, we found out the equation of motion for the radial expansion of the CME plasma, somewhat some complicated equation. So the main highlight point here is that the equation simply contain L, R, or some acceleration something. So these are the measurable parameters from white light observation, and we try to find out the thermal parameter. So in this way, that in using this equation, we can try to fit this equation and try to find out the thermal parameter from using the white light observation. And also, as the CME is a 3D parameter, as a 3D structure, and what we image is a simply a projection image in the sky plane. So we try to find out the true kinematics using a GCS model. So this is a geometrical model. So it takes some geometrical parameters, some positional parameter, and it take the simultaneous image from 3 vantage point to find out the true kinematics. So these are the parameters we derived. So the first three are the forces that are responsible for the expansion of CME, and these are some thermal parameters. Okay, so now let's highlight the polytrophic index. So polytrophic index, like the polytrophic process, is a process that involves the heat transfer, and it can describe the compression or expansion of the fluid. So this is PV to the power gamma equal constant. The gamma is the polytrophic index, and depending on the value of gamma, we can say that the CME is going through which process. So the gamma, the values depending on, like, if the gamma is 0, then it's isobaric process. Gamma equal to 1, this is isothermal process. So depending on the gamma, you can treat the CME go through these processes. Okay. So the observation for the data, we have used the stereo Secchi coronagraph and Soho Lasco coronagraph. These are the field of view like core 1, core 2, C2 and C3. And these are the events we have selected. So let's go to the result. So as I said, the event we took like around 8 events. For now, I'll give showing the results only for the 2 events, and then in the conclusion part, I will conclude for all the events. So the first one is 20 August 2018, and the second one is 24 September 2011. So these are the kinematic results from the GCS model. So the first one, the black one, is simply the propagation height, and the second one is the expansion height. So this is the speed, and the two profile, you can see for the first one, the high speed we obtained something around 400 km per second, but the second one is something 2500 km per second. So you can treat the first one as a slow CME and the second one as a fast CME. And the acceleration profile, as you can see, this is the expansion acceleration, the blue one, and it expand a gradual manner, but here it expand a rapid manner. So you can now onwards, we can treat the CME first one as a slow CME and a gradual expanded CME. And here is a fast CME, the second one, and the second one is a fast CME and rapidly expanded CME. Okay, so this is the polytrophic index result. So as you can see, the first case, the polytrophic index is around value 1 or 1.2. So that it shows the value 1 means it's a isothermal process. So isothermal is the temperature is constant. That means for this field of view, like some 5 to 16 solar radii, the CME maintain its temperature. That means it go through only the like the thermal isothermal process, despite of being like expanded. But for the second CME, we find out like for initially the polytrophic value is above 1.66. That means it release some amount of heat. Then after it again maintain its temperature, like the value is something around 1. That means isothermal process. So to verify that, we also find out the heating rate on the CME plasma, and we find out like the fast CME, the slow CME case, when the speed is low, we found there is a like gradual increase in the heating rate. So as you can see, this one, the heating rate is gradually increasing. But for the fast CME, you find out the heating rate is fast. The initial is negative. Negative heating rate means it release some amount of heat. Then after it's almost like increasing. So we fit it in the power index form, and we found out like the power index this is. So the first case, that is it is to h to the power 0.9. So that means almost linear. So it increase in the linear manner to the height. Okay, so then we find out the temperature profile. So the blue one is the model temperature, and this one is the adiabatic cooling temperature. So we have to compare these things. So if our CME release with this temperature, we find out like if it only expand in the adiabatic manner, then the profile should be like this, the orange one, and the blue one is the model parameter. So you can find, as I said before, in the polytrophic index value also, that if you maintain its temperature, as you can see, it is almost constant for this field of view, despite of being like expanded. And for the fast CME case, also found the initial state, it is the CME, the temperature decrease very fast way, like below the adiabatic cooling. Then it again like gain some amount of heat from the surrounding. Then again it's maintain its temperature.
Good first.
Yeah. So then the forces we found out like Lorentz force, thermal pressure force, and centrifugal force. And in Lorentz force, you can see the for both the cases, Lorentz force is negative. That means Lorentz force is prohibiting the expansion of the CME. And this is the thermal pressure force. It's also like positive for both the cases. That means it helps in the expansion of the CME. And also the centrifugal force is positive. That also helps in the expansion of the CME. And also for all the three forces, we found out the centrifugal force decrease very fast way, and its contribution is only like feasible in the near to the sun. So these are for all the events. So we can see when there is the high speed, the speed is high and the change in acceleration is high, we found the polytrophic index value is higher one. So that means when the speed is the high speed CME, okay, then I can conclude here also. So for gradual expanded and slow speed CME, we found out that the polytrophic index value is somewhat 1 or 1.3 for obviously our field of view. Then that means we found out also that there is a continuous injection of heat into the system, and it maintains its temperature nearly constant or gradual decrease in temperature. But for rapidly expanded high speed CME, you find out like the polytrophic index is value is greater something 1.3. In initial period, it release heat, and then afterwards it injection of heat. And so that result in the rapid fall in the initial phase in the temperature, then obviously maintains temperature and gradual decrease in temperature. So these are some like a general conclusion that the ratio of the Lorentz force to thermal pressure force decrease, and the Lorentz force prohibit the expansion, while the thermal pressure force and centrifugal force allow the expansion, and the centrifugal is important for the expansion near to the sun. And near the sun, like up to 6 to 8 solar radii, we found out there can be injection and release of heat, but after that 6 to 8 solar radii, there is only injection of heat into the system. And despite of like the CME is expanded, for both the cases, the CME maintains its temperature like above the adiabatic cooling profile. So the takeaway message is that for a gradual accelerated slow speed CME, only injection of heat into the system. But for a rapidly accelerated and fast CME, we found out initially there is a heat release and then injection of heat. And the centrifugal force is a major contributor to the expansion of the CME near to the sun. So these are some references. And thanks to the organizing committee for giving the opportunity to give the talk here, and the areas for this nice hospitality. So thank you.
So we can have only one question because we're running short of time.
We talked about the three-part structure of CME, why there is a formation of cavity between leading edge and core.
So like we treat the CME as a flux rope. So the flux rope part is that cavity. So there like the density is low. There is a magnetic field only. But I can show you. Okay, so here this one is like the CME is propagating in the interplanetary space. So around that is solar wind. So that means the plasma is there. So when a CME propagate and ahead of it there is a plasma, solar wind plasma. So it can pile up those plasma so that density increase there. So that's why we saw this increase in density profile. So that looks white, and like followed by that there is a like. This is not like dark, but the like the ahead of thing is that there is a increase in density when it is propagate. So there is a pile of plasma, so that's why it looks bright compared to the cavity one.
Thank you very much. Thank you, Samaranjan. So, our next speaker now is Upasana Baveja. She'll be talking about coronal magnetic field estimation with the influence.
Host disabled participant screen share.
You are co-host.
You might not use. It is getting disconnected.
Speaker, huh? You want to take some time?
I think it will take some time.
Okay, then we go to the next speaker.
Mhm.
We go to the next speaker.
Mhm.
So
Yeah,
take
sure.
a little bit time. I think it's going. ठीक है जी,
ठीक है।
go and sit. So I'm facing some technical difficulties because of Zoom. So we'll push it, let's talk the next one. So our next speaker would be Charita Pan, who shall be talking to us about geo-effectiveness of DHCMs for solar cycle 24. Have the mic.
ये work is
It's forward and backward.
forward and the pointer this one.
Point is this one.
This is forward.
Point is this one, I think.
No.
Yeah.
Right.
Keep hold it. Put and hold it.
Yeah.
Vertically. Easy. Or which one?
Hello everyone, myself Charita Pan from Kumaon University, Nainital. Today I'm going to deliver a talk on myself Charita Pan from Kumaon University, Nainital. Today I'm going to deliver a talk on geo-effectiveness of DSCMEs for solar cycle 24. Now these are my plans of talk. First, I'll go through the introduction part, like what are the solar radio bursts, then their classification, and then I'll introduce you about the geomagnetic storms, what are the factors that are responsible for these storms, then association of type 2 radio bursts with CMEs, and then interplanetary plasma parameters, which are the main indices, important parameters for causing the geomagnetic storms, and at last the references. So here we go, solar radio burst. As you all know, sun is the main source of energy and space weather event of our solar system. It is responsible for all kind of kinetics of Earth, for the for release of energy in the form of radiations, magnetic fields, and charged particle. Solar radio burst is basically an intense release of solar radio emissions from the sun, and that are related to flares and extreme space weather events. They are basically found below a low frequency range that is below 200 megahertz. And Wild and MC Crady in 1950 were the first who observed these solar radio emissions or the solar radio burst in the dynamic spectra, having a broad band which lasts from 20 minutes to few hours. Solar radio bursts are the first phenomena that are observed in the field of radio astronomy. These are basically arrangement of frequency space which varies over time. In this image, as you can see, a flare is coming out of the sun and a radio burst is related to it. And this is the radio burst which is related to this flare. Now, classification of solar radio burst. MC Grady in 1950 classified these solar radio bursts into 5 types, depending on their frequency. The type 1, type 2, type 3, type 4, and type 5. The type 1 solar radio burst is due to the active regions. Type 2 is due to the shocks. Type 3 is due to the Type 3 solar radio burst is due to the moving electrons, and type 4 is due to the electrons that are trapped in moving or stable in the magnetic structures during any eruption, and type 5 is a variant of type 2 only. If we want to study about any kind of solar eruption, so we have to use this type 2, type 1, type 2, type 3, and type 4 solar radio burst. Now coming to the geomagnetic storms. As we know that CMEs are the propagation of huge amount of magnetized plasma from the sun into the interplanetary medium or in the solar corona. So when these CMEs they travel through the interplanetary magnetic medium, they appears on the visible disk of the sun, and they are called basically ICMEs. So ICMEs are the root cause of these geomagnetic storms. When these high speed CMEs when they interact with Earth's magnetosphere, then there is a disturbance in the Earth's magnetic field. Due to this disturbance, the geomagnetic storms occur, and the interaction between these Earth's magnetosphere and these high energy solar wind, which creates a magnetopause here. So this geomagnetic storm is basically a result of magnetic reconnection process, which is taking place here also. As you can see now. So this is the magnetic reconnection process due to which these geomagnetic storms occur. Basically, what is happening here, these two oppositely directed magnetic field lines approaching each other, and they reconnect here, and a kind of sheet is formed here is in this X point, and this is the point where the magnetic field is zero. So we call this as a neutral region. It is also called as a diffusion region. So I have calculated the dimension of this current sheet, like the width of this current sheet, the time at which this sheet is forming, and the rate by which it is forming. Magnetic reconnection process is basically a fundamental process by which the magnetic energy in the sun gets converted into thermal energy and heat, due to which the large temperature of the corona is a result of this. So this is a diagram where it has been shown that a solar wind coming from the sun, and it is bombarding continuously here. This region is called the magnetopause region, and it is surrounding the earth. And this region which is on the front side of the sun, it is called day side region, and this is which is away from the sun is night side region, and this is elongated about hundreds of radii of earth. So we can assume as like water is flowing around a stone in a stream. Now coming to the main part. For calculating the thickness and time and rate of that sheet which is forming due to the magnetic reconnection process, I have used the Sweet-Parker model here. When these oppositely directed magnetic field lines, they reconnect, so the thermal pressure increases, and as a result of this, the plasma moves out in the outward direction with the characteristic speed that is given by this. Now applying continuity equation and using the length scale of that dissipation region, and doing some sort of mathematical calculation, I derive an expression for the width of this current sheet, that is delta Z is equals to ME over 4 mu naught NE square lambda x. Here lambda x is the length scale of that dissipation region, and it is measured in terms of ion cyclotron frequency. Here n is the number density of electrons in the solar corona, and basically it is equals to 10 to the power 14 to 15 per meter cube. So putting these numerical values, the width of the current sheet comes out to be 10 to the power 3 meter. Now doing the same and using the same model, I have calculated the reconnection time, which is inversely proportional to cube of the magnetic field. and also the reconnection rate, which comes out to be 10 to the power minus 6. So after plotting, sorry, after plotting this equation, that reconnection time in the 3D figure, so it shows the reconnection time varies with magnetic field and the length scale of dissipation region, showing that the reconnection time is of the order of 10 to the power minus 8 second. Now, association of DS type 2 radio burst with CMEs. Basically, I have done this for solar cycle 24. I have taken around 119 events where DS type 2 radio bursts are associated with CMEs, out of which 31% are geoeffective and rest of are non-geoeffective. We considered a parameter which is called disturbance solar time index, that is DST index. On the basis of this index, we classify the events as geo-effective and non-geo-effective. Those events which have DST index less than minus 50 nanotesla are called geo-effective and other non-geo-effective. So I have done a correlative study between the correlative study between CME acceleration and the CME speed. This figure is for geoeffective events and this is for non-geoeffective events. As you can see, here is a good negative correlation between acceleration and CME, which is significant, and here it is not significant. So it seems from the graph that CME acceleration decreases as speed increases. So we can say that slow CMEs de-escalate less than the faster CME. So there is an anti-correlation relation between these two parameters. This anti-correlation is due to the Lorentz force due to aerodynamic drag, because when CME passes through the interplanetary medium, they experiences a drag force, and when this drag force dominates over the dynamics of CMEs, they results in the decrease of Lorentz force, which is responsible for this deceleration. Now coming to the main part, that is interplanetary plasma parameters. The geomagnetic storms are measured by certain indices which are called interplanetary plasma parameters, and one main parameter that is responsible for these geomagnetic storms to occur is the southward magnetic component, that is BZ component. And when BZ component is equals to 0, we say that this event is a geo-effective event. So as you can see from figure A and figure D, the correlation between DST index, which measures the geo-effectiveness of any event, here the correlation is greater than 0.5. Here also their product, like that southward magnetic component BZ and velocity of the solar wind, here also the correlation is greater than 0.5. So we can, and this figure also is less dispersed. So we can say that these interplanetary parameters are effectively responsible for the occurrence of the geomagnetic storms. And at last, the result, the fluctuation in solar wind speed causes geomagnetic storms. The DST is basically an hourly average of the deviation of magnetic field from the horizontal component. So it determines the intensity of the geomagnetic storm. When the DST value is equals to 0, it means no deviation. And if it is less than minus 1500 Tesla, then we say that it is a geomagnetic storm. Geomagnetic field indices are determined by interplanetary parameters. CMEs are the main drivers of geomagnetic storms. As you have seen that as CME speed increases, the acceleration decreases. So we can say that this could be the driver of the geomagnetic storm, and southward magnetic field is an important parameter for protection of geomagnetic storms. And as the correlation is greater than 0.5, so these are responsible for the occurrence of these storms. And here are some of the references. Thank you.
Thank you, Charita. Questions? Questions?
You know, to ask.
Yes, 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 please.
So, my question is, you have estimated the time scale for the reconnection.
Yeah.
Why is it important? Is it an important parameter? Or why do you care for estimating that?
because we should know at what time the sheet is forming. Like before, many authors have done the previous work, but they have not calculated such parameter. So I think time.
For the reconnection.
Yeah, I think
It's not the formation of the sheet.
it is the time at which the sheet is forming.
Yeah. So is it the duration that you're worried about?
Duration at which the sheet is forming. Okay, thank you.
Any more questions? Yeah.
So in your second last slide, can you actually say that there is some correlation in these, or you need like more statistics for that?
No, the correlation have been already done.
I mean, if you can see the scatter is like too much here in these graphs.
If we do the power law fit square method, maybe it seems good.
And what about like if you have more statistics?
If we have more data, then we can draw a new graph which will not be so much dispersed.
Okay. Thank you.
Any more questions? So maybe I have one question. You use Sweet Parker model. You also have pet check kind of reconnection, right? It's very fast.
But the pitching model is for fast reconnection, and I have used here the collision less reconnection. The PASTEC is for collision one.
Okay. Sure. That makes sense.
The collision less is basically due to the high resistivity and low length of that dissipation region. That's why the calculated value of the width of the current sheet is only 10 to the power 3 meter. A small one.
Thank you very much. To the next speaker. Another applause again. We now come back to the class now. Hopefully Zoom works now.
Civil participation scheme.
लीव किया था क्या?
हाँ हो गया था.
Yes, so Pasna shall talk about coronal magnitude estimation.
What is this?
The microphone working?
Yes.
Okay.
Hi everyone, I'm Upasna Baveja and I'm here to discuss about my topic, coronal magnetic field estimation using Bayesian inference. So before going into that, let us discuss about the structure of the sun. I think everyone is aware of this. So inside the sun, there are radiative core. Inside the sun, we have core, then radiative zone, and then the convection zone. And from the visible layer, that is the solar photosphere, we have convection zone, we have chromosphere, and then the solar corona. But the fact is that temperature of the solar corona is very high, that is around million degree Kelvin. And also the magnetic field strength inside the solar corona is about 2 to 3 orders of magnitude less as compared to the solar photosphere. So in that case, it becomes difficult for us to estimate the magnitude of magnetic field. To estimate the magnetic field strength, we are using an alternative, that is a coronal seismology. So seismology is basically to use waves to interpret the parameters of the solar corona. So here in this movie, you can see that there are some waves propagating outward. So we are now using these waves to estimate the coronal magnetic field. So for that, we are using this formula where alpha speed CA is related with the magnetic field B and the density rho. So we have to determine the phase speed as well as the density to estimate the magnetic field. So, but the fact is that chronoseismology is an inversion problem, and to estimate the parameters using seismology, we have to deal with some unknown parameters, or in case we have all the parameters, then we have to determine it under some uncertain conditions. So for to have some higher accuracy, so let us discuss all of these things in terms of probability rather than the point estimates. So we will be using the Bayesian inference. So let us first discuss what is Bayesian inference. So Bayesian inference is an approach of parameter estimation and a modal comparison using Bayes theorem. So what is Bayes theorem? So I'm relating with the parameter theta. So if we have a number of parameters theta and we have some model as well as some data, then we can use the prior probability of those model of that parameters given we have some model. And for given model, we can get some likelihood function, and using these two information, we can obtain the posterior probability distribution. And if we have a number of parameters, then we can integrate it over all the other parameters to get the information about one parameter. So that is called the marginal probability. Since we are interested only in the magnetic field, we will determine only for the marginal probability of magnetic field. So let us first determine the phase speed of these waves. For that, we have used the data from COMP. COMP is coronal multi-channel polarimeter, and it observes in iron 13 coronal emission lines in 10747, 10798. So for that, first we obtain the Doppler velocity data, that is line of sight velocity data, and then using that, we filtered it corresponding to 5 minutes oscillation in the solar corona, and we obtained this filtered Doppler velocity data. And to determine the phase speed, since we know that these waves propagate along the direction of magnetic field, so we obtain the wave propagation direction first. So this is a wave propagation map, and then we selected a propagation track of 31 pixels, and for each track, we obtain a space-time diagram of this Doppler velocity. And to separate out the inward and outward propagating waves, we apply 2D FFT on this space-time diagram, and then we separate out the components, and then we applied inverse FFT and obtain these SC diagrams. And after that, to obtain the time lag, we just cross-correlated a time series of the central pixel with the other pixels on the same track. And then we fit a linear model to obtain the phase speed, because the slope of that model will give us the phase speed, and the uncertainty in these parameters gives us the uncertainty in the phase speed. And we repeated the whole process over the whole field of view, and we obtain this wave phase speed map as well as the uncertainty. So first task is done. Next, we have to determine the density. So density data we use from the Yang et al. And then using these two information, we obtain the magnetic field. And before going into that, let us discuss that if we have a flux tube and we have magnetic field Bi inside the flux tube, and outside we have Bo. And similarly, inside if we have density rho I and outside we have rho O. So then this is the phase speed of these waves. And for the low beta plasma, if the pressure balance is mainly dominated by the magnetic field, then in that case, we can obtain the phase speed like this. And using these two information, we obtain the plane of sky component of the magnetic field. So these are the global maps of the coronal magnetic field that we obtain. But again, this is an inversion problem. So we have to use the Bayesian inference model. And for that, we have used this formula. So here we use the prior information of magnetic field as well as density. And we obtain the marginal probability distribution of magnetic field only. For that, we assume that B is varying from 1 to 8 Gauss, and we assume uniform magnetic field distribution for the magnetic field. And for the density, we use two different density distributions. One is a Gaussian and other one is a uniform. And using that, we obtain the joint posterior probability distribution of the magnetic field as well as density. So you can see that this joint probability distribution is actually depending upon the density distribution that we are considering. And if we integrate this joint probability distribution with respect to density, what we got is these marginal distribution plots that is along with these. So you can see that the marginal probability of the magnetic field is actually peaking corresponding to the point where the joint probability distribution is maximum. And in the case of uniform density distribution, we have the joint probability distribution along all the values of density. So if we plot the marginal probability of magnetic field along the different field, points in the field of view, we can see that at some points, the most probable value of the magnetic field obtained using Bayesian inference is actually coinciding with the value that is obtained using the simple inversion. But at few points, it is not actually coinciding. Even the magnetic field obtained using the simple inversion is not even coinciding with the most or the maximum probable value of the magnetic field. And next, if we just plot the most probable values of the magnetic field over the whole field of view, we get these maps. And you can see that the most probable value of magnetic field obtained using two different density distributions is actually the same. And if we obtain the difference between the Bayesian inference and the simple inversion, you can see that the difference lying only near the occulter part, or it is in the outer regions. And we also plotted the 3D plots of the Martian probability distribution of magnetic field. And here you can see that these plots, first of all, these plots are same for these two density distributions. Second, if we can see through this peaks, you can see that this actually corresponds that the magnetic field is probable in these regions, and the color is actually depicting that this color is corresponding to the most probable value of the magnetic field that can be achieved using this distribution. So if we go through these movies of the spatial distribution of magnetic field, where we have plotted the Martian probability distribution of magnetic field with the increasing value of the magnetic field. So you can see that these values, that the higher value, that the probability of the magnetic field is high for the low values of magnetic field in the outer regions, as is clear from these figures. And at around 1.5 goes, the magnetic field is almost structured around these flux tubes. And higher values of magnetic field have more probability in the innermost region of our field of view. So if we plot the radial profile of the magnetic field using the parallel law of fitting, so we obtain that in the east region, where the magnetic field strength is quite low, we can call it as a quiet sun region. So here in this region, the radial profile is the parameter of this radial profile fitting function is less as compared to the obtained on the other side, that is in the west limb. So you can depict that the larger values of alpha in the active region indicate that the magnetic field strength in the active region is decaying very fastly as compared to that in the quiet sun region. And also one more thing, that the simple inversion is overestimating these power law indexes. So coming to the conclusion, we can say that for the first time we have used this Bayesian inference to obtain the global map of coronal magnetic field, and it gives the magnetic field values along with their probabilities, which simple inversion was not giving. And the most magnetic field obtained using simple inversion, that is usually differs from the most probable magnetic field obtained using the Bayesian inference. And also the Bayesian inference gives well-constrained values which have better probability, but the simple inversion doesn't give any well-constrained values. Thank you.
Thank you, Prashni, joining this talk. Questions?
The plot that we have shown.
3D plots,
No, the last one.
radial profile.
You go to that plot.
Actually, I'm on that plot.
Okay, so just like, the two,
Yeah,
Are you able to share your screen?
I have shared it.
sharing is toggle. I think
Okay.
I'll talk to you.
No, you
No,
can
no,
just
no,
ask
you
me.
can ask.
You can just ask.
Yeah, so in that, in those two plots, so I can see the magnetic field, the values for some of the things are quite high. So there's a distribution above the thing that you have made. What is the reason for those? Where there are certain regions where the magnetic field is quite high, but in general, you see them to be, like this plot, this one.
Okay,
Yeah.
this is not shared. So you are asking about these points.
Yeah, those. Yes.
So actually, I just fitted over the whole this region, but
Why over there only you have, some of the
these
values.
high
Yeah,
values.
yeah.
This is due to the reason because if you look closely, this is around 1.1 to 1.15 this solar radii. So in this region, actually the error is quite less. So where the error is less, so at that time actually the magnetic field strength can be evaluated with high certainty. So this is a reason. This is the reason I guess this has in this data.
More question.
So I think I might have missed that. So what were the priors that you have taken for your parameters, and is it like confident by or some observations?
Okay, so I have considered the prior distribution for density and the magnetic field. For the magnetic field, I have used 1 to 8 Gauss and it is uniformly distributed. And for the density, I have actually taken the density data and its uncertainty as well. So using that information, I have assumed that there are two different density distributions, prior density distributions, Gaussian and the uniform one. So these values I have taken from the observation, means Yang et al. They have evaluated those values, so I have considered those values.
Okay.
Very good. Any more questions? So I have one question. So your density measurement would be different as it go across the limb. Right? There is a exponential drop in density. So do you use the same prior for all the points?
Yeah.
Wouldn't
Means-
that be not correct?
I mean to say that I have the information of each and every pixel value, means the density at each and every pixel value. So whatever they have calculated the density, say at each pixel near the limb, I have row 1. And if we move far away from the limb, then we have some row 2. So I've considered the information near the limb as row 1 plus minus a delta row and along with their probability values. And for the far away limb, so I have row 2 plus minus delta row 2. So I've considered the probability corresponding to these ranges.
So your distribution basically is the form of the distribution is same. It just shifts. as
Yeah,
we go across
according to their values.
values. Okay. And yeah, that makes sense. Yeah, then thank you, Pasna. The final speaker for today. The final speaker for today will be Pratik Maya. We'll be talking to us about Swasti, based on the adaptive simulation framework.
Mobile.
You can keep it here.
On है
Hi everyone, I'm Pratik Meng from IIT Indore, and today I will be presenting on a space weather model named Swasti. So first I will briefly introduce the space weather, then I will describe the solar wind model, and then the CME model, and in the end I will talk slightly about the ongoing work, and then I will summarize everything. So space weather is generally referred to the coupled environment of Sun and Earth. It can also be called star and a planet. And as we know that the sun's magnetic field changes, and that brings variability in the Earth's magnetic field. And this whole thing comes under the space weather study. But it is interesting because it has some direct implications on us. It can degrade the electric power quality. It can perturb navigation system, GPS, interrupt satellite functionality, and obviously hazardous to astronauts' health. And some extremely energetic space weather events could even impact global economy. So the question arises that can we stop it? So unfortunately, the answer is no, at least in the near future. So how to mitigate its effect? Can we do that? Yes. So we can do that by doing forecasting. So similarly, if a tsunami is there, so we cannot stop it, but it can we can reduce its loss by using the forecasting alerts. So to do that, we need to understand the physics underlying these in 3 domains, that is solar, heliospheric, and Earth domain. And there are many institutes in India who are working on this problem. And our group is working on heliospheric and Earth domain. And my domain is heliospheric. And from the viewpoint of computational heliospheric work, three things could be done right now in the current scenario. One is developing a model to extrapolate the magnetic field lines from the solar surface to the outer corona, then developing a solar wind model, and then injecting the CMEs and SCPs into that model to predict its duration, arrival time, and etc. So with this motivation, we are developing an indigenous physics-based space with adaptive simulation framework, which is SWASTI framework, whose purpose is twofold. One is the forecasting of the arrival time, the properties, the duration, the threat level of the space weather events, mainly solar wind, SIR, CME, and assessing or studying their propagation and interaction with different space weather drivers. So coming to the solar wind model, it uses a synoptic magnetogram, GONG or HMI, as an input, and provides the plasma properties in the inner heliosphere. So it is based on two sub-models. The first one is semi-empirical coronal model.
Those I think works. It's working. Yes.
Oh, there is a lag. Okay. Internet. Okay. So it has only one input, observational input, that is the GONG or HMI magnetogram. And then we use PFSS model to extrapolate the field lines in the lower corona, and then SCS model in the upper corona. And once we have extrapolated the field lines, and using the magnetogram, we have something called WSA model, which provides the velocity profile at 0.1 AU, so that we get the best result at 1 AU. So we use that and we get the initial boundary condition for speed, and then we use other empirical relations for different things like density and pressure. And then we use the MHD equations to solve the plasma properties in the inner heliosphere using Pluto code. We also use HUX, which is heliospheric upwind extrapolation technique, which is relatively very fast, but it only provides an essence of the result because it only gives 1D speed. So this is the result of the solar wind model, and this is a movie. In the upper three plots are the radial component of speed in R phi, R theta, and theta phi at 1 AU. So in the C plot, the 0 will be the Earth's location. And the one immediate conclusion that we can make from this picture is that we can see the spiral structure of the solar wind, the slow solar wind constraint in the nearby of equatorial region. And in the C plot, we can see a current sheet forming structure where the speed is slow of the solar wind and the magnetic field lines are flipping, and the density is lower as well as density is higher and temperature is lower. So as far as validation with observation is concerned, we took 5 Carrington rotations and chose such that there is no CME present. Otherwise, we would be comparing two totally different things. So we chose 5 CRs. These are the comparisons. So they are matching pretty well. And this is the comparison with 1 hour averaged Omni data. And we also compared other plasma properties. You can see that the magnetic field is matching. It's like moderate, it's fair enough, but the density is getting overestimated and the temperature is getting underestimated. And we also tried to see that if we change the ratio of specific heat, which is gamma, from 1.67, which is 5/3, and if it decreases, then we observed that the magnetic field line magnitude and the density are not changing much, but there is a significant change in the temperature. That's what we observed. So now coming to the coronal mass ejection model, CME. So it is basically based on the solar wind. The solar wind acts as a background, and then we inject the CME structure in the heliosphere. So everything remains the same. It's just that additional technique of injecting the CME in the solar wind. So this is the one Carrington rotation that I'm displaying. It is for the cone model. So basically in cone model, there is a non-magnetic cloud, and the geometry is simple and the cross section is circular. And for simplicity, I've taken the homogeneous speed, density, and temperature of the whole CME structure. So this here is interesting because there are 5 kind of halo CMEs which are strong enough. And the bottom plot is for the radial component of speed in the 3. And in the C subplot, you can see the 0, 0 is the Earth's location. So you can see if the CMEs are coming, then it will be reaching at the point of 0, 0 in the C subplot. So it just hit the Earth, and similarly, it just missed the Earth. So coming to the density and the temperature profile, so you can see in the density, which is the first one, and you can see the SIR structures are forming, and there is a very strong SIR of the very red color in the subplot A, and that is the strong CME, SIR, stream interaction region with a high density. So if we see that the CMEs are coming out, then an immediate conclusion is that the SIR is blocking their radial propagation. So they are kind of de-accelerating the CMEs. But the CME is strong enough to totally destroy it. There are multiple CMEs, so that SIR has totally gone. And one other conclusion that can be made is that the angular expansion of CME and the phi direction is getting blocked by the adjacent SIR. So that's the two things. And the same, we can see that the temperature profile of the CMEs due to the collision in the front of the CME, the temperature is very high, as well as the CME whole structure is also high, but it's inside of the CME is getting cooled. So we compared with the observation. So the top plot is that if we just only use the solar wind model, so you can see that peaks are missing. So the bottom one is if we use the solar wind plus CME or the CME model. So the bottom one is a 5-minute data. We have increased the time resolution, and it can even up to go to 2 minutes now. So in this plot also, one can see that we have missed the 5th CME, which just saw in the movie that it didn't hit the Earth. But in the observation, we are seeing that it has hit the Earth and there is a very high velocity profile. So if we just focus on these two, then the two strong CRs, which was 1 and 4th, we can say that there is a time lag of approximately 2 hours, and the 5th has been totally missed. So this is the current ongoing work, which we are developing the flux rope model using the fried CME. And it is a magnetic cloud now, all the 3 components of magnetic field. And the geometry is also complex. And obviously, for simplicity, right now, we are taking the homogeneous speed, density, and temperature of the whole structure. So this video, you can see that the slice, the plane of the orange color is the MHD inner boundary. And in the Python, we have developed this structure. And if we allow it to selfly expand, then we can see that in the surface will get slice. So these slices get in the inner boundary of the MHD domain, and hence the structure will be formed and it will propagate. So you can see that the BX and BY and the BZ components of this flux rope. So coming to the summary, that we have successfully developed and validated the results of solar wind forecasting model, and it has been published, and one can see the paper, and if you find anything, then you can talk to me. So the current version of Swasti, the solar wind forecasting model, takes around 6 to 8 hours for medium to high resolution, in the range of that, for 1 CR on 48 cores. The current limitation is that it is overestimating the density and underestimating the temperature, as well as it's only dependent on one input, the observation of magnetogram. So if there is something fuzzy going on in the magnetogram, so it will be get reflected in the results of the model. And the CME model, we have developed the cone model and compared it for 1 CR, and it only takes additional 2 to 3 hours in medium resolution. So if we have 6 to 8 hours solar wind, so it will only take 2 or 3 hours for CME run. And the time resolution, as I said, we have improved it to up to 2 minutes. So we are still developing the flux rope model, and that is very interesting. And we'll once it's developed, we'll compare with multiple observations. There are many things. So thank you.
Very nice talk, Pratik. Questions?
You have compared the new simulation with observation at 1 AM, no?
Yeah.
So, are you planning to compare the simulation with observation between Earth and Sun?
Yeah. So actually, we are working on that. Currently, we are comparing with Parker Solar Probe. So we have started comparing. So right now, we don't have initial even results, but we have started comparing with Solar PSP. And there are also some other spacecraft. So we are planning, once we have developed the flux rope CME, so we'll choose such an event which have multiple spacecraft observations. then that
The
will,
difficult thing, actually.
yeah, obviously.
Are you planning to incorporate like the density and like temperature variables?
Yeah, so currently we don't have the input of density profile or the temperature profile of the CME. So we only do the CME tracing using the coronagraph. So once the structure is formed, but we don't know about the thermodynamic property of the. So right now we are taking the homogeneous based on something that it has been done multiple times, and we have seen that yeah, it's fit for the model. So right now we are doing that. But if we get the observation based density or temperature, then that would be very great.
Like density.
At 21.5 solar radius. Yeah, so MAG domain starts from there. So that's the issue.
I'm not from this field, so it might be a very simple question for you. Are you planning to use data from satellites like NASA, GOES, and even Chandrayaan-2 XSM, which will give you separate like these solar flares at different, at least the eruptions at different locations, and maybe even in future Aditya L1 or something like that.
Yeah, so actually we have also simulated the potential observations of aspects, but due to time limitation, I was not able to show. As far as other spacecraft is concerned, so I don't have that much idea, but whichever spacecraft is giving the properties of the bulk, speed, temperature, density, the proton density, then that is very useful. That can be compared.
So as far as I know, you can fit the XSM, the Chandrayaan-2 XSM data and get good temperature estimates, but I'm not fully sure whether that will be the only thing that will be
Okay,
useful for you.
Okay, I will look
But-
into it. Yeah.
Thanks.
You can do that, I think, but I don't think that's for solar wind. It's the remote sensing measurement, right? XSM is a remote sensing measurement of the solar disk. It's not in situ measurement. So, XSM, XSM is basically measuring photons, right? It's a remote sensing measurement. It's not like it's not sitting on. It's not solar wind measurement.
Okay.
So you can't use that to come.
Oh, okay.
Yeah.
Thanks.
You can get the temperature of the corona with that.
Yeah.
That can drive your inner boundary, but I think I don't
Yeah,
need that.
yeah.
Okay, I have maybe one interesting question for you. Do you see switch packs in your simulation?
Okay. So I think the SIR structure is turbulent. So there we can see, but it's like I haven't seen. It has to be higher resolution, and we'll have to look for it. So I haven't done that. So if it will happen in the solar wind in the inner heliosphere, then it has to be SIR region. So that's the turbulent region it can form there.
So yeah, as you might be aware, there are multiple theories, right? Like one can be in situ formation, one can be because of interchange reconnection.
Yeah.
So yeah, I mean, your background solar wind model, the future trajectory you can look at.
Yeah.
Yeah, nice. Thanks.
Yeah,
Thanks for a very
thanks.
nice talk. And thank you to all the speakers for giving on time, giving very nice talks. So, Jay, you have
So let's break for tea now. So I was going to make you all have received mails, I think, for the group photo during this tea session. So if your friends and colleagues are not here, we just call them. We'll be having group photo right after tea. During the tea. We'll meet at 12.
हमें बताएंगे लेकिन वो लिखा हुआ था स्लाइड में लिखा हुआ था बताएंगे
Okay, so welcome back after the tea break. So I'm Vivek. And in this year's jam, as you might have been aware that we have included the significant part of outreach as part of our, YAM conference. So continuing that, so we have basically a dedicated session for outreach activities right now. So in this session, we'll be talking, we have speakers from IA, we have speakers from IUCA and Aries, and we have one speaker from Cosmic Partha. So these guys will present their work, how they have, what kind of work they are doing, and how you can help them, how you can contribute towards their work. Right. So the first speaker is Athar from IUCA. So Athar is basically the part of IUCA SciPop, and he is leading outreach operations at IUCA. So let's welcome Athar.
Yes.
Just borrow your mic.
Hey.
Hello, am I audible to all? At the back too? Okay. Good morning. Thank you for inviting IUCA to give a brief overview of outreach activities that we do. I am Atharva Pathak. I work at the Pune Knowledge Cluster, which is a project under IUCA. And we not only do work in astronomy, but also on other verticals. So moving forward, for those who do not know what IUCA is, so IUCA is a research institute, which is one of the oldest research institutes working in astronomy and astrophysics in India. And I'm sure most of you already do know. One of its mandates is to actually inculcate science interest in students, inform the public, and do outreach. So this is a mandate apart from the regular mandates that research institutes have. So it was one of the first institutes or pioneering institutes to start a dedicated science outreach team and department in its campus. So we have people who have been employed for doing just outreach and have no other major responsibilities. So Pune Knowledge Cluster is one such projects under IUCA, which is established by the Office of Principal Scientific Advisor. And the idea is to bring industries, academia, and civic bodies together and run some projects which will give meaningful solutions to the day-to-day problems. So these are some of our partners, and we constantly keep on collaborating and working with them on various projects. This is the current, branches. These are different branches of IUCA. IUCA currently hosts the IUCA SciPop, which is the primary outreach effort. And I am here on behalf of IUCA SciPop here right now. And we ran a couple of activities in collaboration with Aries in different schools over the last 3-4 days. So we have Vigyan Tarang Lab, which is a lab set up by Padma Shri Arvind Gupta. And it emphasizes on creating space and science toys to explain or effectively explain astronomy and science concepts, typically to students and teachers. Then we have Astronomy Center for Educators, which has been quite newly established. And the aim of this is to train teachers and educators to eventually start BSMS courses in their own universities and colleges, or BSMS electives in their own universities and colleges. And IUCA will facilitate training such educators. Then there are different mega science projects out of which the IUCA is a part of. IUCA also has a dedicated office of Astronomy for Education, which caters to the training and education resources for K-12 students. So up to 12th grade, we design and develop different resources, and we run them in different schools in and around Pune. And depending upon the outcome, we scale it up. And IUCA has a dedicated outreach associates program. So we have collaboration with 80 universities in India, and being a IUC helps us do that quite effectively. We also have partnerships with OAD and OAO, Office of Astronomy for Development and Office of Astronomy for Outreach. So which are two more IUCA bodies, IAU bodies, which run different outreach efforts. So our forte is basically school level science teaching and outreach. And we have a dedicated astronomy outreach, vertical in the science outreach department. So we, on an average, reach out to more than 3 to 4 million people per year. So combined in a mixture of offline and online programs. So these are some of the highlights where we have reached different people in different programs. So typically on the National Science Day, we have around 10-15,000 visitors who visit us in person. And we usually hold the Science Day on only one day. Sometimes it's 2 or 3 day long program. Then we also have a quite active social media presence on Twitter, Facebook, YouTube, and Instagram. Most of you already may know it, but you can just give a quick search for Ayuka or Ayuka SciPop and you'll find us. These are some more collaborations that we have. Some of the projects that Ayuka hosts or runs are AstroSat, Chandrayaan, LIGO, TMT, SKA, Aditya L1, and Pune Lois Cluster. And we often partner with different agencies which are involved in building these projects. Now, today I will mainly talk about how you can plan your own astronomy event and how can you reproduce whatever we are doing in your own institutes or in your own clubs. So we often make use of some techniques for effectively reaching out to the audience. We do something called neuro-linguistic programming of school students, and we identify which students are visuals, which students are kinesthetic, and which students are auditory. So those of you who don't know what this is, so there are some people who are more perceptive to visual inputs than auditory. Some people read and remember things. Some people, let's say if you're traveling in a car, you tend to remember the places rather than the names of the places. Or if somebody tells you address over the phone, you are more likely to understand that better. And there are some people who are kinesthetic who need to do things. Probably when you are attending a lecture, if you have a habit of writing things down, then you are a kinesthetic person. Then you need some input where you have to actually work or do some hands-on activity in order to understand things. So these we have such tools and questionnaires and some activities that we run and do NLP analysis, after which we disseminate respective resources to the students. So these are some tools which you might already know. So we make extensive use of free and open source tools as well as mobile applications, and we also train students, teachers, and people who visit us in effectively using them. This is another very interesting technique, which is role play based learning, where you can actually involve audience in playing different roles. Like for example, these teachers are planets and they are moving along an elliptical orbit, and they're observing how they move faster when they're closer to the planet and slower when they're farther away. So we also run a couple of citizen science projects. We have created some of our own, and they are called 1 million galaxy project, where the idea is to classify galaxies based on their morphology. And we have currently 1,200 citizens registered to us, and our idea is to ultimately classify 1 million galaxies with the help of these citizens. And the outcome of this should be AI ML model, which will then learn from whatever inputs that have been received from the citizens. And in future, if we give it a larger data set, it should do the classification on its own. So for astronomy event or astronomy plan, what do you need? You need a good astronomy event idea. You should have ample resources, which are human, logistics, technology. You should also know your exact audience, and then there is a follow-up and publicity. So before 2020, it was actually much easier to plan and run astronomy events before pandemic, if you will. So it was actually very easy to go and interact with people, plan events. Now it has been restored back to that normal, but these are some of the activities that used to happen. The numbers were quite high pre-2020. So these are some of the outreach activities that we do. There are school visits, there are campus visits, then there are teacher training workshops. We have outreach activities dedicated to projects. You can see 30-meter telescope model in the center. Similarly, we have a LIGO working model in Ayuka, at least the scaled model of LIGO in Ayuka. On the bottom right-hand side, you can see the Ayuka 14-inch observatory right after the photometric observations were done. And then there is a science day, and then there are public talks, which are something regular in Ayuka. There is another interesting thing which brought me into astronomy was the second Saturday lectures. So it is what happens on every second Saturday, except monsoons. So school students can visit Ayuka. They can attend lectures from different students, different PhD students or faculty in Ayuka, and they can directly interact with the scientists and also see very interesting demonstrations of science and space toys. So then we also have created a lots of good resources on how you can live stream your events and how you can use broadcasting, editing, and streaming softwares quite effectively to demonstrate your work and also to make your presentations much more interactive. So these are some of the programs that we have run during the pandemic. So these were some moon challenge where people should step out of their house safely and observe the moon, and then we would give them some resources which will then involve them or engage them in some activity, and then there would be some outcome to it. So we keep on running different like competitions as well. So there was a science fiction writing story writing competition which was judged by Professor Jain Narayakar and Mangala Narayakar. Then there was there were many online events that we hosted while collaborating with many institutes. Some of them are already here. So you can see some people from IIA, some from ASAC. So this was an annular solar eclipse live stream. We keep away releasing such tidbits and updates on social media, especially WhatsApp. So where we give away the local words for some astronomical terms and their meanings, along with some photos. So this it's like the word of the day thing. Then we also have organized amateur astronomer specific event where how they can contribute to professional astronomers, what all activities can they do, and how can they be directly involved with institutes like Ayuka and maybe even generate internships and observational opportunities. So these were some more dedicated programs. One of which was Introduction to Basic Measuring Instruments. So we took basic measurements and we created a series on it along with some activities as well as models that they can build, and they can understand what is the least count, what is the error, how can they do effective measurements and all. So the age groups that we target are always varied, and then there are always programs which are mixed for all age groups as well. So this was the online teacher training which got a great response. So usually Ayuka teacher trainings happen offline where we invite teachers around Pune. For this we got a response from all over India and also some from outside India, and this was a very successful program. So how they could use Android applications or science toys with low cost materials or technology or all these things were incorporated in these workshops, and the outcome was quite effective. So these are some more activities that we would like encourage you to explore. Ayuka has a telescope making program where you can run that program in your own institutes. You can have people visiting you. They can build and make their own telescopes, and then you can make some observations of moons, planets, and even some amateur observations of maybe occultations as well. Then there is a thing called Bring Your Own Binoculars, where you can ask people to bring their own instruments and engage them in sky watching activities, so that they can basically enjoy and they can understand that how fun sky watching really is, and it will also help you to enjoy it. So then use of radio or TV or podcast or webcast. So I already see many of the PhD students are already starting to engage in these things where they are creating their own webcasts or podcasts. Or now there is a beautiful initiative called Cosmic Varta, where they are simplifying the research that they do to a layman language, and that is something very effective and very important. So that can be scaled up by making use of these platforms. So there are a lots of so this is the second last slide. So there are a lot of resources which have been compiled by IAU, which can definitely add quality to your work and it can help you do outreach. There are also a lot of India-centric resources which have been compiled and consolidated by ASI POEC. But now you can also work with your local institutes, your peers, and you can create your own content like particular to your own institute and add it to that set of compilation of resources. So these are the prerequisites we think we need to have to do effective outreach. So there should be a very, very good network of peers like us. Then there should be a very good relation and access between scientists and students. There should be open resources. If there are very nice and very effective resources that you build, they should be made open so that a wider range of audience and people get to use it. Then there should be contests which generate a friendly competition between students, and it often increases the reach of your activity. And some dedicated events specific to astronomical phenomena, or some events like National Science Day. So I welcome your questions or suggestions. So you can find more about me here, and you can write to us on this email ID. We'll be very happy to take your suggestions and questions. So our Facebook. Thank you.
So let's take this figure. So we'll have some questions.
Yeah.
Hi, Tarvar.
Hi.
Thanks for the great intro to IUCAA Cyber. Just curious, how are you trying to go forward with the network of all astronomers in the country? Is there anything planned?
So IUCAA has this thing called IUCAA Associates. So our next planned activity, which is not yet out in the public, which is very well streamed now. So we plan to collaborate with these associates and have run a series of programs at their local levels. So we will create a program structure where we will define it quite well what all needs to be done in those programs, and we want to run those same programs in all different regions and study how effective that is. If not, then we will make some tweaks in it, and then what we really want to do is we want to engage common public directly with the associates and tell them about what work goes on in astronomy. And for that, we are creating some dedicated resources. Some of them are video resources, some of them are games, some of them are mobile applications and all that. So that is how we are planned right now. So we are going to utilize the IUCAA associates first, because they are easily accessible to us. And eventually, with the help of PhD students like we have here, we would like to scale it up.
So there was just one quick suggestion there from my side, is that we have a lot of these astronomy clubs in institutes all over the country, and maybe we can, your team can leverage onto people from those clubs, because they have usually a very good network within their own city about what school to target and where exactly to go for such events that you will be planning. So that will be
Okay, thanks a lot.
Any other questions? So if there are not any questions, let's thank the speaker again.
Thank you.
So the next talk will be contributed by Virendra Yadav. So he is a scientist at Aries, and he is basically he's leading the outreach activities of our institute. He is also part of the POEC. So collaborating between the POEC and Aries, we have done some outreach activities. So he'll be highlighting those things. Virendra.
Yeah.
साइड में अगर टैप कर लीजिए। Okay. So again, good afternoon, everyone. So I'm Virendra, and I'm here to talk about the outreach activities that we do at Aries. Now, I will be also, sort of sidetracking a bit somewhat at some point of the time because of the overlap with the POEC's activities also. You already know that I am also part of POEC and presently the co-chair. Devendra is the chair. You already heard his talk yesterday. Now, again, these are not any technical talks. These are some descriptions, some strategies that we utilize, and some views that we have come up with during our experience with outreach. Slides are not having- Go back. Hey, go back to that. It's already shared, I think.
It's not sure.
Achha, screen is not shared. Okay. Back. Go go back to that. Okay, wait.
इसको next करेंगे तो हो ही जाएगा एक बार।
Achha, you try. Guilty here because till the time I was sitting there in the corner, I was still modifying some of the slides. So I finished just now. Okay, anyway. So whenever we do outreach activities, still not moving. Yeah, it always helps to start with this image, particularly to when you go to schools and colleges or people in planes, those who are not familiar with AV, they look at what place we are located and how this institute looks like. And this dome is what the people who are moving on the way to Nainital, they easily identify and they become curious. Oh, what is that? They ask the cab drivers, "Arey, wo kya hai? Can we visit?" When they come to know. So the cab drivers, obviously to earn more, sometimes even say, "Din mein tare dikhate hain." You get to see the stars even during the daytime, and sometimes they get disappointed. But yeah, I mean, at least they get to see the observatory telescope, the 1 meter telescope, and we talk about that telescope also. And we have a small planetarium, so some planetarium shows are also there, and they get to learn more about. Through simple videos. This is not very sophisticated planetarium. It's a very small planetarium, and the planetariums that you might have seen in metro cities, they are much larger, much more sophisticated. Here, the biggest restriction that we have, obviously, you can see here also, is of a big open flat space. So that's why all of our facilities are scattered throughout the campus, and whatever facilities we have, they are usually small in size, smaller capacity. So same is true with our science center as well. But the advantage is that we have an observatory telescope located right here. We have a ST radar located right in the campus,
So these facilities, and sometimes we also take people with some prior arrangement to Devastal also. So Aries facilities, right in the campus, they give a big advantage that people just get blown away while looking at such huge telescopes. Then the science center, basically a center for visitors. This is the planetarium near the science center. Some of you, those who are staying in the campus, you might have walked across and might have noticed this building. There we have small telescopes which we usually use for outreach events, and some science posters, some models. Although the models are kind of a bit of old models, something probably the today's younger generation may not be that interested in. But yeah, we are also looking to upgrade these models and acquire new models and work on simple science toys, and that's why Atharva's presence over here has been helpful, and we'll be collaborating more in future for these, and he has really agreed for that. And in the earlier times, we also used to have a science and technology book counter, which was where we were representing Vigyan Prasar. So Vigyan Prasar has this lot of nice book collection in English, Hindi, and other Indian languages, where they explain simple concepts in layman terms. And we used to have that counter here as well. A hill station at a remote place, at a a small town. So you have to be sensible, or you have to keep this in mind, whom you are talking to. Okay, we cannot assume that or we cannot present or do outreach in the same manner as IUCA or TIFR would do in a metro city. Okay. So in the BCE days, and by BCE days I mean before COVID era, the local attraction, of course, we were a big attraction in Nainital. Every year we used to have 7,000 to 9,000 visitors over here. Of course, IUCA gets that in one day on Science Day. But again, ease of access to this place. We are at a pretty remote location, so it's not very easy. So, and this number comprises roughly around 60% of school college students, and the remaining 40% used to be the tourists who come to Nainital, for vacation and holidays. So student visits were attended throughout the year, and general audience, although they were open throughout the year. I mean, when I say throughout the year, again, the 4 months of monsoons are pretty much, sort of excluded, because the rains are also extremely heavy over here and humidity is very bad. So general audience, the numbers, peak a lot in April, May, and June, the peak tourist season, and October, November as well. And whenever there is a celestial event, so that time also there is a huge influx of people. Now, some of the pictures that I'll be showing you are only from the next or the last 2 years or so since I joined. I joined in December 2020 only. So, but the outreach activities have been going on for a much longer period of time by my predecessors at this place. And of course, these people were scientists, so they had their own research, they had their PhD students to take care of, and this was an additional responsibility. In whatever little time they could manage, they did it very well. And you can say the second person and another person was a technical staff who was taking part in this outreach activity. So right now we two are the members in this team. So the BCE days, this used to be the number of students that. So for example, during solar eclipses, we used to get something like 200 to 400 students in a day. So I mean, imagine at such a small place where you don't have any big open space, but still it was managed. And you see here, outreach being done at different places on different occasions. You have dot here and ST over here. Then, as I said, I was talking about being sensible to or being mindful of the place you are in. So here, even now, print newspapers are a piece of information or a tool of gathering information for general masses. They are still very popular. Metro cities may nobody buys newspapers anymore, but still a lot of people buy newspapers here. So print media is really important in this place. So whenever there is a
a celestial event. So people from here, they write short articles and share with the print media team or local journalists. And some of them who repeatedly did that, they became so interested in this that whenever there was any event, even if there was no article from here, they would find out something about this. They call up someone over here and they will find out more information and they will write an article by themselves. So this also has happened with our 2 and 3 journalists, and now we just have to give them small piece of information and they will come up with a pretty decent article. I mean, of course, you cannot expect a proper scientific sort of article where everything is 100% right. But yeah, more or less they are doing good job. And similarly, for the past few years, these research articles that come out from Aries, and this has been done by other research institutes as well. This is nothing specific to us, but these research articles, they are being conveyed to the media cells in Department of Science and Technology, and they propagate it at the national level as well. Then in CE era or the COVID era, this was the situation. Everything has to be done online. So there were a lot of lectures. This was a popular lecture series. More than 20 lectures were given by age members. This eclipse was during the COVID era. And I'm specifically showing this event for something interesting. I will show that a bit later on. So we had clouds for some time, and then courtesy IA, we had showed their feed and some other celestial events. So this is the Jupiter-Saturn conjunction over here, and there's the same picture. There's a comet. So many of so this is taken from the god. This is by I think Vibhuti's image. Is research scholar over here. Just finished his PhD, and yeah. So some other celestial events. Then again, National Science Day also was done mainly in the online mode. And so why I was talking about specifically the COVID period, that so some online talks and all documentary screening and celestial events were shown. And yeah, I would probably sound like an influencer here. But obviously these numbers are pretty minuscule as compared to the number of eyeballs that IIA's channels or IUCA's channel gather because of being in a metro city. So why I was specifically showing this? Obviously, when the lecture series online things were new, Zoom and this was popular, so many people were attending this. But after a few months, COVID fatigue or online fatigue or Zoom fatigue set in. And it was like I had to really, ask Aries students to participate at least in some of the outreach activities online, so that the speaker doesn't feel bad that there are only 20 people or 10 people. So yeah, that also had happened. So, so we had a workshop last year, this at IIA, which was astronomy outreach activities during the pandemic time, and for that I had worked out these numbers. So you can see here. So this used to be, so before there were very few online videos on Aries social media channels about the dot and Aries. So the numbers were pretty high, and these numbers were accumulated over a period of say 2-3 years. Then the e-lecture series. So yeah, there was a small spike, completely flat. Solar eclipse in 2020, a big spike. So obviously celestial events and particularly eclipses, they gather a lot of eyeballs. So they are really, really good opportunities for doing science outreach. Then slowly as the pandemic eased in, the hybrid or online mode activities or in-person activities also were started. And so these are some snaps from Science Day activities. So this is a balloon launch that usually happens on Wednesdays. So when school kids are visiting, the teams hand over the balloon to them and they themselves launch it. So it gives a nice involvement to the kids, and they also feel interested in the activities rather than just coming here and listening to someone blabbering. Yeah, again these some online activities, theme-based activities, because then if you take advantage of whatever is going on. So for example, world's World Space Week or World Environment Day or International Women's Day. So if you're doing theme-based outreach activities, that is helpful in gathering more views and more eyeballs, because ultimately our aim is that we should reach to larger and larger number of people. Then exhibitions, through different organizations, different departments, we get requests to participate in exhibitions, and as much as feasible, we participate in these exhibitions. Although these exhibitions are not that good from outreach perspective, because you don't get that much time to interact with the students, you don't get one-on-one time. I mean, there might be a gathering of say 5,000 students, and they will hardly get 10 to 15 minutes on a stall. So it's not that good of idea, but still at least they get some exposure, some familiarity, and this way you may be able to reach even places which are far off. Then again, I was talking about celestial event. So the recent eclipses were examples. So these are some newspaper coverings. I purposely cut short this half image over here, because it was talking about even though this is an eclipse, the temple's doors will be closed and this and that. I didn't want that to be highlighted over here. But this was during the solar eclipse only. This is, you see Professor Banerjee, distributing sweets. So we did arrange for some snacks, and we ourselves had it, and we also asked the visitors to have it. Because this is really important. I have even seen scientists believing in such things, space physicists and astronomers, that you should not read during an eclipse. Astronomers. Okay, so that's why, I mean, if astronomers or scientists are believing this, you can't expect it from general people, right? That they would not be believing in such silly things. So that's why whatever we are doing is really important. The reason why we are doing it, already yesterday we had spoken about it in much more detail. So just quickly, a glimpse of whatever was done over the last 2-3 days is that some of you agreed to participate in the initiative by PUEC, that there will be some outreach activities where you will be talking to school kids. And Ayuka and Aries helped in arranging those programs and activities. And these are some newspaper clippings and some snaps. I have shown only a few, but there are tons more. If you follow PUEC's social media posts, you will see that many more pictures will be coming soon. Now, where we are lacking, if you compare us with West, so it's not possible for everyone to go out and spend a night and do stargazing for the whole night. So this is one good activity which Western countries have been doing for a very long time, particularly US. And that even for smaller, not only eclipses, even other celestial events, they do virtual events. And in fact, Ayuka also has done some of these events, I remember. And so this could be a good possibility. It's worth exploring. Probably this year's Gemini meteor shower or somewhere we'll try that. I already did once during one of the lunar occultations of Mars. So again, to sound like an influencer, subscribe to Aries social media channels, PUAC's social media channels, Ayuka's IA's social media channels. Not only because you already know whatever is going on, but you also are connected to a lot of people through your social media accounts, right? So if you just share whatever is being done, so maybe say 5% of your friends, if they see that, who are from not scientific background, it will be helpful. Okay, and it would also help grow the footfall or eyeballs for outreach activities by various institutes as well as PUEC. So that's what I wanted to convey. I missed mentioning one point that yesterday when Divyendra was talking, that we should also try to pull politicians in somewhere. There was one very valid question by one of the participants over here. So exhibitions are one point where you can do that. Of course, they will hardly spend 5 minutes at your stall, and whichever stall looks more attractive, probably they will go there. But at least that is where you can spend some time. And there are some people who are gracious enough to spend more time, and they are really interested. In fact, just few weeks ago, we had 50-year workshop of this 1 meter ST. And the governor of Uttarakhand, he was really kind enough that during his previous visit
in I think June or July when he visited this place. He himself said that he would like to felicitate 50 people who were involved in the 50-year history of the telescope. So it was his own initiative, his own idea, and he kept that promise. So that's why it's really helpful. And that's all. I would like to thank my predecessors who have done all the outreach activities.
Thanks, Vijay. So now we'll take a few questions from the audience.
Yeah.
Yeah, you talked about virtual solar observatory, virtual night watching. Huh?
Yes.
Yeah. Apart from that, what are other plans from Aries side to increase the outreach activities in Aries and collaboration with other institutes? What are your plans?
Okay. So as far as collaboration is concerned, so through PUAC, we all are involved with other institutes, and some idea sharing is already happening. Okay. Now, of course, I am also not a trained science outreach specialist or science communicator. So I also have been learning it from the other team members and outreach teams in other institutes, planetarias, and science centers. Now, one straightforward example of collaboration was just now, you already experienced it, the outreach activities during YAM, where Ayuka and some members of Cosmic Varta, Vishal, so we had gone to different schools. Now coming to the outreach activities that Aries is planning. So as I already said that since we are located at a remote place, it's not very feasible for a lot of these schools to come here. Although we do get a lot of footfalls, I mean, comparatively, if you compare with the nearby population. When I talked to some of the schools in Haldwani, many of them, they said that they have never been here, even though they are barely located some 30-40 kilometers. So although schools in Nainital, they have visited frequently, but in Haldwani that has not been the case. Similarly, whenever we do these Science Day activities or the 1 week Science Day celebration, we see the numbers are not that much, because ultimately we have to reach to larger and larger number of students, right? That's the aim of these activities, not to show how many activities you have done in the institute's profile. Ultimate aim is that only that you have to reach to a larger and larger number of people. So the science outreach activities, usually we get participation from schools in Nainital, which are, the schools are a bit well off. They get a lot of exposure already. But what I am looking forward this time is that what Ayuko also has done for the past few years is that going to different schools, making them as a center for some National Science Day activity or some competition, and invite nearby schools. So we'll be doing something like that to also increase the outreach activities, or the number of outreach activities. Will be also increasing the team strength pretty soon, probably within next 1.5 months. There will be advertisement for one additional post. So yeah, sorry. So if you have your friends who are interested in something like this.
So Virendra is our own, I mean, he's here. So if you have any questions, you can just catch him during the lunch and during the day. He'll be here only.
Yeah,
So
about this or about POEC, yes.
So you can continue discussion later. So we are running lot of time now. So we have 2 speakers left. So now next is Vishal. So Vishal is a PhD student at Ayuka, but he will be talking about his work with Cosmic Varta, a platform to simplify research. So Vishal.
Am I audible?
Yes.
It's changing. Is there a pointer? Oh,
Point is busy. Okay. Anyway, so thank you, Vivek, for inviting us or inviting the Cosmic Varta for in this first occasion. So I've interacted with almost all of you, I think, but I don't remember anybody's names. So apologies for that. So yeah, this session has been extremely fruitful, and this whole meeting has been very fruitful, especially in terms of science outreach. We have been doing a lot of science, or all of us are doing very good science, but it all means nothing if we can't disseminate that to the public.
because people think, even I was coming here from Banaras. So when I find that this cab driver from Haldwani, he was asking me, आप साइंटिस्ट लोग तो ऐसे कुछ भी करते हो, अपनी दुनिया में रहते हो, आपको पता है हम लोग क्या कर रहे हैं. So the perception which a public has of a scientist is basically somebody who is very much drowned in their work, which is true, just not, I'm not saying it's not true, but that also reflects a very important emotion in people, that this science that we are doing, whatever is being done, is very unreachable to the public. And that is a gap that is not something that public bridges. It's a gap, something we who are students at least. So researchers who are all faculty, they may not have time to do this, but we as students who are seeing both the sides, who are coming from one side to the other, we know how the public feels and various levels of the public feels. And so it's our job, I would say. And since we're also working on taxpayers' money, it's a duty to disseminate science to people. So Cosmic Varta is one such initiative of promoting the science that is being done in India to the public of India. So the importance of astronomy outreach has been covered excellently by both Atharva and Virendra. And both of them have emphasized on the fact that the language that you use to communicate depends on the crowd that you're communicating. So you can't use the same, it starts from the grammar that you use, it starts from the tone that you use, on what is your intention to communicate. So all of this is very different depending on the crowd. But our main aim as Cosmic Varta is to disseminate the current research being done in India. So it is not just a generic, so one thing is to inspire people about science in general, about astronomy in general, astrophysics in general. The other thing is to look at what science is being done right now and what new things are being done and put that out to the public. So our idea basically was to make findings of research accessible to everybody. And we sort of started last year. We started actually exactly a year back. And we wanted to start off with something very simple, not very complicated. Because you can dream big, but you start big, you're just going to fall down. Build step by step. And so our preferred medium was written. And the journal articles that we write, sometimes even we can't understand what is being written. So there was an article recently on the kind of sentences judges make. That you have these long lines without any full stops, and you just forget what is happening in the first couple of letters when you come to the end of the sentence. So this is how typically judgment statements are written, and that is how a lot of papers are also being written. Like you have a huge paragraph, which is basically just one line, and you just go crazy after reading it. But you learn that. I mean, as students, we are all learning that, and we are sort of used to it. The public is not used to it. The public needs short, simple, sweet information that comes out in discrete bits. So we do that. Public understands at least some aspect of what is being done. So translating journal articles to popular science articles is what we have been doing over the last full year. So today is 12th, and exactly a year back we went live on social media. So yeah, so basically what we do is our primary forte is publishing popular science articles, but we also have interviews with eminent astrophysicists and scientists, because again, people seem unapproachable. All these scientists are doing something in some cave somewhere. This is what the public feels. But these scientists are very much humans. They're all accessible. You can go and talk to them. It's not difficult. I mean, of course they are busy, but you can actually go and talk to them. So interviews with scientists and astrophysicists is one great way in which you know the thought process behind what goes in that person, what the person wants to do, what the person does. Also, we provide information related to universities and institutes which conduct research in astronomy and astrophysics. So I'll come to what these various things are later on. That is our website. So how many of you have seen the Cosmic Varta website? Can I have a show of hands, please? Okay, that's quite a good number. Yeah. So this is our website, and if you are interested in the website, just scan the QR code there. Or if you are the old school person, you can just type the whole link there if you find. So we basically have a bunch of articles, and there are two kinds of articles which come up. There are featured articles, and then there are these new review articles. Review articles are basically papers which have come out very recently, and the authors have written up distilled the whole paper into a simple article. Featured articles could be interviews with scientists or summaries of meetings or a list of scholarships, or even very high impact papers. So, for example, when Professor Padmanabhan passed away last year, we had a featured article by one of his students on typically what work Paddy sir did. And that was a very extensive article. It was a very sweet and a very nice written article. That's a featured article, summarizing the life's work of a very eminent scientist. So that's our website. And one of the important things on our website, which we have tried to compile, is this career help, which lists how would you, if you want to do astrophysics, how would you go about doing it? What are the institutes that you might apply to do astrophysics? So this is an evolving document, right? As we keep getting more information, we keep dumping it there, and it keeps evolving over time. So there's one place where some things are consolidated, and it's you may refer this to any person who may come to you and ask you, "Arey Devi, how do I do astrophysics?" No, people do that. No, we went for outreach the last couple of days. Children were coming and talking to us. They're asking us, "Sir, I want to be an astronomer. What do I do?" So I can't just share this link here right yet, but I can share this link to the teachers of those children, and then the teacher distills the information for the students. So that's how these things work. Because once the adult knows where to start, the kids can then follow. So yeah, and there are various such interesting, important links. If you're a new grad student who has not had much experience with coding or getting things started, you also have some stuff for you. How do you use IDL? How do you use various data services and things like that? So typically, when you start, when you're a grad student in the first year or something, we're all lost. We don't know where to start because there are so many things. We're just overwhelmed. So we have some resources at different places. Again, this is an evolving document. This is like a living document. It keeps evolving over time. And we're on social media, on Facebook and Twitter. And whatever new article comes, we have a social media post on both these profiles. And a couple of numbers, just to since Cosmic Vata has been live for a year now. There are around 46 articles, with around 5 featured articles. And mostly the contribution has been from PhD scholars and master's students. There are also some postdocs and scientists who have contributed to our articles, but mostly it has been PhD students. They got a new paper out and we send them a request. Or many a times, these students have sent requests to us that, I have a paper. I would like to write a popular science article. And that is very heartwarming that, people are so enthusiastic to take their work to the public. And typically, we have been receiving contributions from institutes, but we do have a substantial contribution from the universities, which tells us that the good work happens in universities also. It is just the exposure that the university students get towards science outreach. And it's very heartwarming to see that the university students are also able to, find this space. And I would encourage everybody, whenever you get a new paper out, to write a popular science article on your paper. So this is the number of views. I mean, okay, there's a bunch of different statistics here and more statistics here. So this statistics here corresponds to what was the views and everything last month. And I'm pretty sure you can't read anything from the back. But the general idea is that the articles on the first page have been read a lot. And that is obviously noted. And then the article about Cosmic Vata, what it is, that has also been read a lot. But then if you look at the articles over the last year, one of our most read articles was a list of scholarships for women in science. So during February, we had this day on International Women's Day, International Day of Women in Science and Technology. So on this day, we compiled 2 sets of articles. One which traces the life history of various women scientists and the struggles they have had, in the hope that it inspires girls today to take up science. And the second is a bunch of is an article on the list of scholarships and various initiatives by the government and non-government agencies for science education and education in general at different levels of education. So from school level to college level to even postgraduate level. So we had compiled these 2 sets of articles, and we really were happy to see that this article, the list of scholarships, was very well received by the public. And we are trying to make this a much more extensive database. Make it hashable. You can just query. You can put in your requirements that I am doing this. Now tell me what are the scholarships I need. I can actually apply to. That is something we are working on, and we need people to work on that. So yeah, it is interesting to note that the reach has not just been in India. So the articles come from India. The research has been done in India. or at least done by Indians. But then the reach is also from other countries. So people from other countries are also looking at our articles, and but obviously by and large it's from India. And this large spike that you get, that is on the International Day of Women in STEM. So when the two articles that we had put up, we had gotten a huge spike, and it was crazy the amount of viewership we got on that day alone. And typically we find users from Bangalore, Pune. So you can see that there are metro cities with a lot of researchers and scientists and students which are who are basically reading our articles. So typically how our process works is we have a 5-step process. We curate or we trawl archive for new papers, especially on papers which have come from India. And then the team members start emailing the authors. This is typically how it goes, but sometimes the authors mail us themselves. And then once we get a positive response, the author starts to write a new article, a popular science article. And then we have an editorial team. A lot of editors are here also. So we run through with the authors a couple of times on simplifying or distilling the article. Some people are great. They already have they have already written these articles, so they know very well how to write popular science articles. Some people are just starting, so we help them out in and try to simplify these articles. And finally, this article is published online, and there is a lot of propagation being done. So there are different roles that are important for throughout the whole process. We need a project and a website manager. We have the authors, that is you, who will be writing. You also have the editors, who you could be an editor also. So you can author a couple of articles. You can also edit a couple of articles. Like for instance, I have done. And we also need social media manager, so who manages all the social media stuff. The short-term goals of Cosmic Varta is basically to make it self-sustaining, in the sense that as we keep getting new articles, we keep pushing them online. And then we keep having featured articles for any specific events or interesting, important events. The interviews and reaching out to universities is something we are doing right now, and things start coming up soon. But we have a lot of long-term goals that we need to have. We plan to have a proper career guidance set up on the website, put up online, and publish proceedings of different meetings online. So one of our pet projects is to have something in regional languages. So you can see everything is in English. So obviously the reach is only going to be in some metro cities or all of these English-speaking elite places. But the common public is not so English savvy. It needs to be told in the regional languages. So translating these articles to regional languages is something that we are looking forward to. And how can you contribute? You can be an author and write an article. That's the most obvious thing. You can be an editor and edit other people's articles. Once you are well accustomed to how to write a popular science article. And then as a mentor, you can help us. So even we are all students, right? So if you are very well versed in how science popularization is being done, you can help us, you can mentor us on how we can make things better. You can always make things better. You can also always volunteer or join our team as a project manager, as a site manager, as an editor. And finally, you can, if you don't want to do any of this, you can just spread the word. You can just tell people, oh, there's something called Cosmic Varta. Right? That's a very easy thing to do. And we have a couple of guidelines. I just skip that. And we had a couple of talks at the ASI. We had a virtual get together with people who came to ASI were interested in working with us. And so we had a bunch of talks, and we have a talk here right now. So that's the core team, a bunch of people. Vivek was there for a long time now, and he is now moved on. So yeah, and then we have an editorial team. So these are some people who have been editing a lot of articles very consistently. But there are many more people who have been editing a lot of articles consistently, and and this team has been growing and growing and growing. And so one thing, finally, I would like to thank, or we would like to thank ASI for helping set things up and for inviting us as a part of ASI celebrations, and a lot of people to acknowledge, because so this is not a team which is led by one person, or no, it's just like a one-person initiative. It is the community. So I will go after some time, right? So I'm a transient being in this team, and somebody else will take up. So you people, especially the more younger students, you come in, take up the initiative, and then you lead the team. So that's how the whole team evolves. So yeah, thank you, and I'll be very happy if you can contact me. You can just contact me or contact us at Cosmic Varta, and then we can take up the initiative.
Thank you, Ishak. So now we have time for one or two quick questions. Did you have any?
So apart from this popular science article, are you planning for any podcast with different scientists to popularize different cosmic events or something?
So we have plans like that. It's just that we are running a bit low on manpower. But the idea is that the current, so this is how it goes. So we can always write articles, that is fine. But the current public has a very short attention span. So podcast is the next best thing you can do. 1 hour podcast, some people can listen, but most people just doze off. And the next best thing you do is these Instagram posts, like a bunch of posts, people just look at it and swipe and be done with it. So these are the level of things that we are looking at. So for the same article, for example, we can also have podcast, a quick summary with a video or something, or an Instagram post. Interviews with people, with scientists is something we're actually planning. We have a couple of people in works. Yeah, we're thinking of it. Yes.
Yeah. And also, you were talking that all the people are joining your team. Maybe they are the transient members. So how can you transfer your ideas to the future generation? Because you have some ideas how to grow and how to develop all these things. Now, how can you transfer your ideas to the future generation that they will follow the same trend or they will find something different?
Good, Vishal. Maybe we can
We can take it later on.
forward.
Yes.
Here.
Yes,
You're
yes.
running late on time.
Yes, absolutely. Yes, absolutely. Yes.
So the next speaker will be Crispin Karthik from IA. Sorry for the delay, Crispin. So
Fine.
yeah, so
There was a delay from. Okay.
wait, Crispin now.
Can you allow me to share?
Oh, yeah. Yes, Crispin. You may try now.
Okay. Up to what time? Right now it is 1:07.
We have 15 minutes approximately.
Okay.
You can wind up early, it will be better for us.
Okay. Okay.
So Crispin will be talking, he's the scientist C at IA. So he'll be talking about the outreach activities done by the Institute of Astrophysics in Bangalore. Crispin, you may go.
Yeah. Thank you. One minute, please. Is it visible?
Yes, we can see your screen, but we cannot see the slides.
Okay. Sorry. 1 minute.
Yeah, so can you try sharing again? We are just looking at just some sort of a wallpaper right now.
Okay. 1 minute. Was that? Shall I read out? I think there was
So you may
some.
try resharing it. We cannot see your slides.
Okay. Let's see the- 1 minute.
So yes, now we can see the slides. You are muted.
Is it okay now?
Yes, we can hear you now. Please go ahead.
Okay, with no delay, I'm going to the topic. Okay, so this is about public outreach activities at IE. And thanks for the invitation. Okay, so whenever we are talking about outreach, of course, varied outreach, we are keep on doing on it. And but if we categorize into some sketches, like my video is not on, that's okay. So yeah, so it will be like this. Okay, so when we are talking about astronomy outreach all the time, so it goes like to whom? So there are academic people and there are non-academic people also. Then if you categorize into the academic people into separate categories, like there are beginners and intermediate and advanced who is going for the college. Within the school itself, you can categorize into two categories. And of course, teachers also coming and associated with the parents who were, they will also get to have a knowledge. And there is another category, amateur astronomers, who is very good in all the technical details and astrophotography and everything. And enthusiasm always will be there. So the other category, like public people who is settled and their life, I mean, they are into the another stream of their life and stuff. So if you go with the result of that, whatever we are going to the we are making in an outreach, so it will come like this, like the academic people. So hope so my cursor is visible. So it is like a being subjective for motivational purposes. So they will be motivated.
Sorry to
Yeah.
interrupt you. Are you moving the slides?
No, I'm in the second slide.
Okay, so we are looking at the first slide only.
Okay.
Yeah, so maybe you can try full screen. Then.
He has shared all the points instead of he has shared only the slide presentation.
Okay.
He has to share the books in the desktop.
Yeah. Now we can see the second slide.
Okay. Now what is in title slide? This is second slide, right?
Yeah.
What is now? Second slide.
Yes,
Okay.
now slides are moving.
Okay. So yeah, when we are categorizing, it is academic and non-academic. Academic into the education people, schools and college going, and always the output comes like the students will willing to be a scientist or being into the academic field, and that will end up with whatever we are doing. It will become motivational for them and encouraging to them to be in the field. And we can also identify the proper talents to be, to get into the field and part of a scientist community. And there is another thing. There are people always comes like a hobby. Okay, so they are interested, but the star and galaxies and the universe by watching the science fiction movies and the documentaries, all these things, but they may not know that what is exactly we are doing and physics point of view also. So they are like either through the N2, of course, there are people who is motivated and learning the physics. And so it is, we have to identify such those people who is really get into the subject and topic and then coming into the field. So that I have put it like a funny save or so, like there are they shouldn't be misguided or they shouldn't be attracted without knowing the physics background. So that case it helps to segregate the talents, and we have to channelize them whether to come here and academic or make it as a hobby, that kind of guidance. So we are responsible for that. And another thing is like amateur astronomers in the public. So of course, that is always whoever is not into the field or career, that will be like public people or educated people, uneducated people. So for them, it is like enlightening the society or breaking the myth, whatever the eclipse related things they are having, or just to know like save the planet Earth and regarding that responsibility also. And another thing, the academic itself, there is always one more category who is into and being into academic, and then to the always we are into the goal of the scientist and the market, job market in that case. So So that also better along with outreach, it's not only the knowledge we are giving and the enlightenment we are giving or making them people to attract to the topic. It out of that we have to make them to logic. They should be good at logical and reasoning skills. So it's not that only the scientist part. There can be a assistant professor and they can do wherever go and they can make use of it. This particular thing I really wanted to say because there are people who is missing the track and suffering. So just for that I want to say. So when we are doing, it's like a flavor sweet. We are giving outreach. So people are attracted coming, but we have to show the path and categorize and reach them to the final target. And okay, coming to the ways of outreach, what are the outreach? Like one is we can invite them to our place and showing our facilities and etc. And wherever the people who is having that facility, we can reach them and going to the school and colleges and we can make an outreach activities over there. So that's how all of us were watching in the previous talk and all. Okay, again there are comes so after COVID comes, this online becomes famous. So there is online and offline. Then the programs, like how are the programs we can categorize. One is the of course series of astronomical talk and what is happening and updating with the society. And another one is activities based.
Sorry to interrupt. Are you still on the second slide? Because we are still
Yes.
seeing the second slide.
Okay, I'm going with that chart. Hope so the chart is visible.
Yes. Fine.
Okay.
Then continue, please. Yes.
Okay. So it is on the right hand side. Okay, so this is like activity based also we can go with, and then the event based. So what are the event based? We can go with the night sky watch as a regular. Always moon, I mean the moon craters and the planets. We have to enlighten them that also. Like whenever people are coming, they want to see the star or something else. But of course, we know that it is being in the maximum of moderate inch is 8 inch. So after above that we can go, but the planet Jupiter, Saturn, and the moon, and these other things possible stuff we have to enlighten them. And then always with respect to that position rising and setting, we can find out the calendar within the calendar which day it is available. So we can conduct such events. And of course, whenever the comet comes or any solar eclipse or lunar eclipse, that becomes like a celestial event. And other than that, we can always go up with the program like National Science Day or the other programs. So this is one of the best, one of the example for the solar eclipse. And okay, I am okay, introduction slide I had to say. Of course, you have seen Dr. I'm Krishnan Kadi. So I was in from 2019, and then we started a separate section called Scope, Science Communication Public Outreach. So right now we are in channelizing. We are at a separate section, and we are building it. And before outreach was there. So this is the Kodaikanal solar eclipse picture. And again, when I'm saying that receiving and reaching, then we are approaching the people through the online form. There are two types of forms where people want to visit us, they can fill the form. Otherwise, if they request we to visit them, and there is another form to fill them, that it is always the form is filling up. People are coming only on the field station. Always, this is whatever I'm talking about the IA main campus, but always we receive more number of people at the Kodaikanal field station and the Vainupop observatory also. So it's we cannot even conduct like a separate event because the crowd is such a massive. So it always and Kodaikanal being a tourist place, always people come. And out of that, it is Bangalore thing alone I'm talking about. So we ask how do we engage the people? The once they come, of course, with the video lecture and the short presentation, we'll make it. And then there is a photonics division visit where the optics related thing and the illumination, the mirror, that also they can see, and the celestat observation where projection of the suns with the sunspots, all these things. But we are trying to go with the new H alpha filter, other telescopes also plan to get it more. And this is, I said, like in the chart, like mandatory programs like there are programs which we have to conduct. Those are the above things, and the middle is what are the astronomical events and receiving the schools and reaching the schools, and with respect to the astronomical calendar. And this is like exhibition stuff where thing, and of course through media, whenever the media suddenly comes on events, and we have to update with that also. This is the picture of the lunar eclipse, and this is the massive structures like the solar eclipse during the COVID time, where we made it right use of that solar eclipse, which falls on the India. Last 3 years, we are lucky that 2019, 20, and this 22 also, it exactly happened to the India, and we had to wait another 9 more years, the next to come. We utilized exactly when it comes to our side, the India part. And this is the Jupiter Saturn conjunction. So this is a typical setup like how we did on that date. And these are the, of course, another way of reaching the people is with designing the very good looking posters and updating with the social media. And we have reached very good subscribers in the YouTube and the Facebook and Twitter also. So and this last year, this year we tried to make, whenever we are saying that calendar, and what are the celestial events happening with that, then we put up onto everything into the calendar with all the details. It was really useful. So this also can be one of the things we can promote our thing to the people. Of course, the year comes, always people interested to get the calendar. So this is another way of getting to them. This is the typical picture and people involved, students, all the students involved in that National Science Day program. It was challenging when we conduct through the online programs, especially the quiz and other stuff. And these are the crowd for National Science Day. National Science Day, we almost make it as a open to all, like all the time the gate will be open, like program, full day program. People will be coming and going with the more number of students. Like that, we conduct the standard like this essay writing and the drawing and other program, and nights watching also. You can see in the bottom of the picture. And we have added upon this another thing. We have a prototype dome where the telescope kept inside, and people are happy to see. I mean, whenever they are watching the video, they are always interested to see in the live person. Either we can connect with the BBO or the Hanley live stream. I mean, showing the movement of the telescope and etc. Otherwise, meanwhile we can also have it on the campus on the terrace. So those are the pictures. This is before I mean the years before 2017. We also conducted the past days like this teacher training program also, because when I'm saying that in the second slide, if you notice, like who are the category of people like academics. So in that case, like teachers also can be concentrated, so that through the teachers it can go to the pupil. And these are all special occasion, like when so one of the time Cambridge visited, so at Ladakh, and these are the activities where the previous students, like among by the students who made it those times with this do it yourself kind of activities book. And this is again once conducted with a series of lectures and mentors. And one more thing you might have noticed in the recent last year Corona time, science stories also. So that was completely engaged with the audience. So this is I was just happy to show this statistic, like something unique, that if you see the age group always 18 to 34, 35, so more in number. So we can understand that what they are really expecting. Of course, most of them are in the career oriented. So that kind of people are more following us and watching us. And this is just to show you the percentage. Yeah, and thank you. And here I want to say that only hope so. This slide I made it the second slide. Is the final sum up of everything, like the category of the people we are reaching and inviting to them, all these things. Yeah, I hope I'm on time. Hello.
Thanks for the
Yeah.
So, do you have any questions for the speaker?
I think everybody in lunchtime.
Yeah, we are already we should be 20 minutes past that.
Yeah.
So let's thank the speaker again. Kristen, thank you for presenting the talk about IIRB activities. So let's take for lunch now and we'll meet at around 2.
Okay, thank you for inviting me. Yeah, yes. Okay, I can leave now. Hello?
Yes. Go ahead.
Yeah, thank you.
Okay. Okay. Recording stop. Recording stop. Leave करो ना, leave करो हो जाएगा। हाँ, leave करो।
बीच में चला
पर मैंने जो इंटरनेट चला था ना, तो
ठीक है तो
ज़्यादा बेटर होगा क्योंकि कुछ चलता रहता है यूट्यूब पर हम लोग मुझे लाइव से चला ही देते हैं ठीक है इसके पीछे से होगा
Hello everyone, welcome to the last contributory talk session of YAM. And in this session, we will have around 4 talks, and our first speaker is Mr. Gaurav Banerjee, and he will be talking about the understanding the disk evolution of classical B stars using multi-epoch optical spectroscopy. So, Gaurav, you have 12 minutes to finish your talk, and I'll give you a reminder at 10.
Forward, backward, pointing. Pointing is this one, first one.
Yeah, you have hold and pressed.
Press and hold for a while.
Yeah.
Okay. Okay, am I audible?
Yes.
Yeah. So good afternoon, everyone. I'm Gaurav Banerjee from Christ University. So our area of research is basically understanding emission line stars studies using spectroscopy in different regime. As I will be like to present our recent work on understanding the disk evolution of classical B stars using a series of multi-epoch optical spectroscopy where we have taken the data from Kavalu Observatory. So I worked with Supervisor Dr. Blesson Matthew, Paul KT. So let me progress. As we know, following Kirchhoff's laws, stars generally show absorption spectrum, but there exist some stars in the universe which also show emission lines in their spectrum. So this is a photographic plate representation where we can see the emission lines here. So what does that indicate? These are interesting stars, which we broadly call them as emission line stars, and they can be classified into various categories: young stellar objects or young pre-main sequence stars, main sequence stars like classical B, Hardwick B, T Tauri. So basically, what these emission lines, where do they form? These emission lines actually indicate that there is existing circumstellar disk which is surrounding the central star like this. So this is the disk, and this is the disk. The circumstellar disk is the place where the emission lines from various elements do originate. So out of these emission line stars, mainly the universe consists of various kinds of emission line stars, but most of the emission line stars fall in the category of the first category, that is classical B stars. So we study as a group mainly classical B stars, T Tauri, Hardwick AV, and my work is on classical B stars. What are basically these kind of stars? Classical B stars are basically B-type main sequence stars. They are the most rapid rotator non-degenerate stars in the universe. Their rotation speed is much higher than any normal non-degenerate star. So basically they have stars or only space objects which possess a circumstellar disk, which is a decretion disk. The disk can vanish anytime without warning. Also, the disk is fully made up of gas. It has no dust component in it. It's a gaseous disk revolving around the star in almost Keplerian motion. So these stars are basically main sequence B-type stars. And if you see our galaxy, it's estimated that around 15 to 20% of the B-type stars in our galaxy are actually classical B stars. So this classical B star was discovered more than 150 years ago, first classical B star. Till now, research is going on. Until now, there exist so many interesting problems related to these stars, which we don't understand. Some I have highlighted in this section, why we should study classical B stars. First of all, they are natural laboratories where we can study the star disk physics, circumstellar disks. As they contain gaseous disks, we can observe them using ground-based facilities easily. Second, I have mentioned that these are very fast rotators. So stellar rotation, which is maybe the only fundamental parameter of stars, which we understand very less. So we can probe stellar rotation by studying these stars. Also, there are so many aspects related to specifically aspects of classical B stars. First of all, we have said that these B stars do possess a gaseous disk, but we till now do not clearly understand how these disks are formed. They are definitely formed from the star itself, but what is the full process, we till now don't understand. Whether a B star is inborn B star or a B-type star changes to BE, or all B-type stars during evolutionary phase changes to BE, we don't understand the evolutionary phase of BE stars. And as I have also mentioned, these BE stars disks are actually transient in nature. They can suddenly vanish without any kind of warning.
we do not understand what this transient nature of BE stars. So our study basically focused, our present study, to understand the transient nature of a selected sample of classical BE stars. If we take the spectra of a BE star, typically the spectra of a BE star looks like this. Obviously, there are certain elements, hydrogen series of lines are very strong, H alpha being the most prominent. There are certain other elements, like sometimes we see Fe2 and O1 are very common emission lines features. Sometimes we can also see silicon features. We can also see the calcium triplet here, like this in rare cases. So this is a, if anyone wants to go through this particular paper, you can go through. We have studied using HCT spectra, a large sample of classical BE stars, where we have studied all major emission lines present in a large sample of field BE stars. Now, while doing this study and while we were doing the literature survey for classical BE, we found that there exists some important aspect which we can follow up. So in my PhD, one part of my PhD was dedicated to that follow-up study. As we see that mostly classical BE stars, if you take the spectra, H alpha line will be present in emission. That line can be of different shapes, but it will be mostly in emission. But in some cases, H alpha line can be in absorption. But it's the classical BE star through literature survey or through proper study, we know it. So this, if we see a classical BE star showing H alpha in absorption, that means that might indicate that the disk is not present star at that time of observation. Disk is not there. So that means this is, so if we can go on studying, or if we can go on continuously monitoring H alpha line profile for a sample of classical BE stars, then we can study this transient nature of BE stars. That is exactly what we have done. So this is what actually transient nature is. So basically the disk of a BE star can suddenly disappear. Again, it can reappear. We don't know the disk formation, disk dissipation timescales for the BE stars. All BE stars do not show such transient nature. Why, we don't know. And many BE stars do show this suddenly. So that's why if we study a particular set of classical BE stars for a long amount of time, then we can ultimately probe this problem, that what is the transient nature, what is the disk dissipation and formation timescale for BE stars. We tried our best to do that. This is some of the literature which you can, very prominent literature where you can find. There are already studies which exist where some particular BE stars showing diskless state has been studied by several authors. During our previous study of field BE stars, we also observed that one among the 118 stars which we studied, it showed H alpha in absorption. But in literature, previously it has shown properly, it is a classical BE star, it has shown H alpha in emission, but when we observed, it showed H alpha in absorption. So we became motivated, and we also found that till now there is no literature which exists where continuous monitoring of classical BE stars has been done, monitor the H alpha line profile study, and to understand their transient nature, at least for 5 years also, 5 or 10 years or 6 years. So we took a target for 5 years, and we progressed to select a sample of 9 stars, 9 bright stars, which will be observable by the 1 meter telescope facility at Vanuatu Observatory, Kavalur. And since 2017, basically since 2015, we took 140 medium resolution spectra for these 9 stars. Out of these 9 stars, 1 were selected from our previous study, which showed H alpha in absorption, and rest 8 were taken from literature, maintaining the observable limit of this telescope. And all those 8 stars are well-known classical BE stars, but they have shown H alpha in absorption at least once in their lifetime through literature. So we selected like that. So this IRF and all these things are used for these basic standard routines for reduction. Programming is used for analysis. So I will directly come to the main results here. This is a wonderful picture of Vanuatu Observatory. So this is actually the 40-inch telescope which we used. I have spent most of my time very nicely in this place. More than 150 nights of observation we have done during my PhD time only from this telescope. So it was a wonderful time. So basically, let me directly come to the observation which we have done. So total number of stars were 9, total 140 spectra we took. And these were the representative sample spectra for each star which we took. So we can see from this table that 4 out of our 9 stars here are showing actually H alpha in emission, but the rest 5 are showing H alpha in absorption. If you go into big details, yes, 4 stars actually show H alpha in emission. I'm not going to, the emission can be of single peak, double peak, without going to the details of that. We observed H alpha in absorption in case of 5 stars, H alpha in emission in case of 4 stars. But if we go on taking multi-epoch spectra, if we want to measure what is the H alpha equivalent with variation, we have found that little or moderate variation exists. Mostly the variation is within 20%. So basically, stars will not behave according to our wish. When we are taking the observation, it will show something great. It might not happen. But from that, we could receive some interesting facts. So out of our 9 stars, we actually, through our proper analysis, we found that our study suggests 4 of among these 9 stars, the first one, is possibly hosting a stable disk at present. One star, this HD 23302, is a famous star, Electra, in Taurus constellation. One can see it with naked eye now, means in the evening. So this HD 23302, this might be passing through this formation phase when we were observing it. And the rest 4 stars, these 4 stars, they were probably undergoing disk loss episodes while we observed it for these stars for 5 years. How we did it, details can be found in our present paper. So yeah, I will just give a glimpse how we did it. This is the case 1 for a stable disk scenario. So if you go on watching, this is the time series spectra of, or this is the time series data for almost all the H alpha profiles which we have taken. If you measure that, we have measured the Kovalevich spectra shows the H alpha equivalent with varying between -23 to around -20 angstrom. In our previous study also, we have found that this star shows H alpha weak emission. But as I have mentioned, all stars were taken considering the fact that at least some author has shown or found H alpha in absorption. So for this star, H alpha was found to be in absorption in 1999, 2013 also. But in our case, we found that this size is almost stable, disk is almost stable. If you go to a case of second case, suppose there are some stars, 2 stars where we found H alpha in weak emission, always in weak emission, H alpha equivalent with always remaining within -5 angstrom. One can tell me, okay, I am not finding H alpha in emission here. So it's a tricky case. Just watching H alpha in absorption doesn't mean that H alpha is actually in absorption. The H alpha can exist below the continuum, that is hidden field in emission. So we have to do some simple exercises to take out the H alpha component, whether it is actually in emission or not, or actually in absorption or not. If you go to the third case, this is the disk formation scenario for the star HD 23302. If we go on, when we went on monitoring this star, we found that this particular star's H alpha equivalent weight is gradually increasing within a time scale of around 43. Our study suggests that this formation for this star is happening for the past 9 months, from 2018 to 2019, for the past 9 months. Another example is disk dissipation. This is a very clear-cut example of disk dissipation. So for this star, one can easily see the H alpha equivalent weight from here to here gradually as time progresses, H alpha equivalent weight is gradually decreasing, which gives an idea that disk is dissipating within a time scale of 43 months. I will not go to the details. This is a same similar scenario for another star, disk dissipation. So let me come to one interesting fact. After that, I will end. For this particular star, which we found HD 60855, for the first time, we actually detected through our previous study that H alpha is in absorption. So this is, we have represented the spectra here. This was the HCT spectra, which we took in 2008, January 11, the first case. When we went to the literature, there are some archival data available for this star. The spectra is available. Interestingly, we found that somebody from Spain, he found that H alpha is in proper emission. And this is the second case. So we found H alpha in absorption. They found H alpha in emission. Through Kovalevich facility, we always found H alpha in emission. So this actually shows within only 2 months, January 2008 to March 2008, within only 2 months, the star has shown H alpha, complete formation of the disk, which is very interesting. I will not go to the details of these cases. We have also classified our stars according to the H alpha epoch-wise variation or overall variation of H alpha equivalent width. So one can go to our present paper and see, this is the summary, this is the archive link of our paper. One can go to this paper and check what is the details, and we can also discuss later. Obviously, future scope is possible. This is our team who studies BE stars. We have collaborators from various places. Well, some important references. Thank you, everyone.
Question for Gaurav?
Hi, Gaurav.
Hi.
Nice talk. So, these are these the result of these B stars are still accreting?
No, B stars are main sequence stars. They are not accreting stars. So these disks are somehow forming from the star itself. One reason is there are theories. One reason is definitely extreme speed of rotation, but extreme speed of rapid rotation cannot account for the whole matter being flown out of the bulge area or equatorial area. Then there is non-radial pulsation, so which mila ke this forms. Now this disk does not contain dust. It's the main sequence star. Gaseous disk forming from the star and dissipating away sometimes.
So it could be result of like stellar confined in a
Stellar wing, non-radial pulsation, rapid rotation, सब कुछ मिला के magnetic field for B stars we haven't found yet. Only one B zeta tau.
Another quick question. Do you see any stellar jet around this?
If there is these B stars are in circumbinarity, yeah. So if there is a compact object attached to this B star nearby, we can see there are sometimes stellar just coming from the compact object, but not from the B star because it's main sequence star, normal B type stars.
B star can be show any UV axis?
Yes, they show UV axis.
That UV axis show any binarity or any other things?
Mostly we predict that UV axis comes from hot companions, binarity. Hot companion. But till now, yes, this is another aspect where we should focus. There is a program where we would like to take up in future is we will search for hot companions of the stars using this through the study of our spectra and through the study of their UV axis. So if you plot the SED, UV axis exists.
Arvind, I think you can continue in the discussion.
Oh, okay.
Any B star found any UV hot combination?
Only one example of one B star having a probable white dwarf, but not confirmed.
Okay, we might not have time for more questions. And thank you, Gaurav, once again. And so the next talk is by Gurpreet Singh, and he'll be talking about an X-ray study of coronally connected active eclipsing binding. Yeah. You have 10 minutes, sorry, 12 minutes, and I'll give you a reminder after 10 minutes.
Yeah, okay. Let's start. So, am I audible? I don't think so.
Yes,
अच्छा अच्छा Okay, so hi everyone. I am Gurpreet. I will be talking about the X-ray study of coronally connected active eclipse binaries. So this is a brief outline of my talk. So I will just briefly discuss about the background, then the star, and these are the analysis and results. Then finally the takeaways. So for the background, so just if you can imagine a star, rotating star, which have a convective envelope, then such kind of a star will have some interesting property that is and it has been found that the rapidly rotating stars, as the period of star increases, then the X-ray activity also increases, and it eventually becomes saturated at about 4 days. And if you want to see where is the sun, it would be somewhere here. It is a pretty inactive star in context of other solar type stars. So if it was rotating very faster, then it would be saturated. Like if it was rotating 27 times faster than now, it would be like 10,000 times brighter in X-rays than it is now, brighter. Okay, so Okay. So an interesting problem would be like if two such stars come close to each other and such that their corona starts contact is in contact, but their photospheres are not in contact. So this particular system we will call as a coronally connected system. So these kind of systems you can find in short period binaries where both the stars in the binary are like late type stars which are active. So it can form a CCB. So again in this diagram we can predict where these coronally connected binaries would be. So they would be somewhere here in a saturated regime. So then the theme of this talk is like how would sun behave if it was a CCB. So here is a cartoon representation of the system. So XY UMA is a system. It is an eclipsing binary which is at 80-degree tilt. So it has a G2 type star which is like just our sun, and a K5 dwarf is just a companion of this star. So and this is a very short period binary, like a half-day period. These are the masses and radius. It is the system is simply like sun is in vicinity of a star, and the vicinity is so small that the corona of both stars are in contact. So okay, so the system was actually observed by XMM Newton simultaneously in UV and X-rays for nearly about 2.5 orbits. So here you can see the UV and X-ray light curves where there are 3 flaring episodes have been observed. And after the removal of flares, what we do is we phase solder the light curve so that you can see the eclipses in UV, and even you can see the orbital modulation in X-rays. Okay, so one thing you can notice is that the UV emission in the maxima 1 and maxima 2 are not same. So that indicates that one side of the binary is slightly more active than the other side of the binary. And we also found that the UV and X-ray emissions are positively correlated, though this correlation is very marginal. Okay, so as you all know that the UV emission is a composite of emission from different layers of a star. It could be coming from the photosphere or from the chromosphere or somewhere else from the transition region, depending on the temperature of the star. So to get the composition of the emission, what we can do is we can simply like sum of the photospheric contributions from each star. Because we know the theoretical photospheric spectra of stars, we know the spectral class, we can get the photospheric theoretical prediction of the emission processes, and we can just simply multiply it with the response function of the telescope and then a dilution factor of b square for the distance. Then we can get the flux, which would account for the photospheric flux. So this is the observed flux we found from the UV emission. And when we do this equation 1, and we found that this particular equation 1 corresponds to nearly 50% is coming from the photosphere of the star. So I don't know what is the fraction for the sun. So if there is any solar guy, he can tell me. I don't think anyone has done this kind of study. Okay, so the next thing is a coronal imaging. So as you all know that the eclipses are completely geometrical phenomena. So if you take this into account, then you can simply invert the light curves from the first principles to get the information of the 3D structures which are giving you the light curve. So what we have done is there are a lot of methods, and we have used the maximum likelihood method used by the Sierkowski, and we have extended the method so that we can take care of the inclination or angle of the binaries. And we have used the reference we have used the grid of 0.1, 0.1 grids, and which are going up to one stellar atmosphere above the photosphere. Okay, so these are the diagrams. These are the plots we got from the coronal imaging, and you can see that there are the top view and bottom view of the binary, and these two are the side views of the binary. And here I want you to see that there are like active regions in between the binary components. These are the X-ray active regions, and they are coming because of like the magnetic field is coming from here to here. There is an intra-binary Okay, so there is an intra-binary active regions which are corresponding to the coronal connection. This is the first time we have seen a coronal connection in any binary systems. So here I have plotted some distributions where you can see that this coronal connection region is nearly twice as bright as the secondary component, whole secondary component. And one interesting thing is that this is like G2 type star. And this G2 type star has a pole dominated corona. Just like our sun, we have the active regions are like in low latitudes. But in XY Uma, we have the sun has like pole dominated corona. So this is something we don't see in sun. So, and again, this is like primary is like 4 times brighter than the secondary. It is just nothing. So further, we have done the phases of X-ray spectral analysis, and we found that the quiescent spectra is well explained by the 2 temperature plasma component, where the temperatures are like 3 million, coronal temperatures are 3 million and 11 million Kelvin. And the coronal abundances are like 14% of the solar photospheric values. And interesting thing is that the quiescent corona is dominated by the hotter plasma component. Like the 11 million Kelvin component is dominating around the system. The quiescent luminosity comes out to be like 10 to the power 30. If you see the sun, then this thing is like 10,000 times brighter than the sun in X-rays, but similar brightness in the visual band. So anyway, what we did is for the phase resolved spectral analysis, we divided the system quiescent corona in terms of in phase bins of 0.1 to see the spectral evolution, and we these are the spectral parameters we got. And for the variability analysis, we found that the luminosity and emission measures are not variable. And the coronal temperatures are basically coronal temperatures and abundances are not variable. Emission measures are. So basically, sorry. So this thing actually indicates that the both stars are due to the coronal connection, both stars are active at the same extent, irrespective of the spectral class of the star. Okay, so you can see that the NH is increasing during the primary eclipse. So that thing is basically the galactic, and this NH basically explains that is there any cool plasma between the source and the star on the observer. So this is increasing. That thing could indicate something. So I will explain it. I think you can read. So so we have done the 3-flare analysis. So we found that the flares are occurring around the primary eclipse, and it is quite possible that these are originating from the coronal connection. And this increase of NH is basically coming because of the recurrent CM is happening on the system. So this coronal connection is giving the rapid flarings, frequent flarings, and these flarings are increasing due to these flarings there are CMEs. And since these CMEs are happening around the same phase, so the quiescent value of the cool plasma increases during the primary eclipse. So you can see that the flares are not that flares are bright, but they are quite variable. They can increase up to 11 to 33% from the quiescent value. So finally, the takeaways, you can read that if you want. Okay, so thank you. So if you are interested, then you can go through for other CCBs.
Okay. Since you are done.
Yeah.
Okay. Any question for the speaker? Anyone? Okay. So if not, we'll move to the next speaker. Thank you, Rohit. Thank you. So our next speaker is Himanshu Dayali, and he will be talking about evolution of silicon dust during star and planet formation.
Could you enable the screenshot?
Yeah. Himanshu, you have 12 minutes to finish your talk. I'll give you a reminder after 10 minutes.
I hope you can hear me, right? No. Okay.
You just take your microphone, just like that.
Is that okay?
Yeah, yeah.
So, hello everyone. I can see the effect of last day of conference and post lunch as well. But I'm going to tell you about the evolution of silicate dust during star and planet formation. So what we have done is we are doing a survey of the nearby star forming regions, and we are trying to study the dust properties of in the protostars. So what I will do is I'll first explain you the problem, then very briefly I'll explain the analysis part, and then I'll directly go to the results. So So how does star formations happen? So like in the morning, Professor Gopinathan has already told you in detail, so I'll be very brief. So star formation starts with the collapse of a rotating molecular cloud due to its self-gravity that leads to formation of a central protostar surrounded by a disk. And at this stage, material from the envelope, surrounding envelope, it rains down on the disk, and and also the material from the disk get accreted on the protostar. And accretion jaha jets. So jets and outflows are also launched in these stages. These stages are known as protostars. These class 0 and class 1 you can see here. So as system evolves, the envelope dissipates away. It gets settled down on the disk, and then material starts from the accreting from disk to star only. And it is this stage that sets the initial condition for the planet formation as well. And further, as system evolves, the disk also dissipates away, and we are left with a mature planetary system like our solar system. But where does this building material for stars come from? It comes from the interstellar medium. So the dilute gas and mixture of dilute gas and dust lying in between the stars in our galaxy. So interesting thing here is that dust by mass is only 1% in ISM, but it plays very important role, very crucial roles in like interstellar chemistry and star formation as well. And it is also the primary source of the opacity. So what does this dust in the ISM is composed of? So predominantly the dust grains are made of silicates. These grains can be amorphous or in crystalline form. And based on their absorption feature, you can distinguish between them. So the amorphous silicates, they show a very broad and smooth absorption features. While if you look at the crystalline absorption features, they are very sharp and narrow. But what about the dust in ISM? So here is an absorption feature of dust. At 10 micron, you can see this is a silicate absorption feature, and it is also known as the standard silicate absorption of ISM. You can see that this absorption feature is very broad and smooth. Means dust in our ISM is amorphous. Also, there is an upper limit by Kemper et al. In 2004 that maximum crystalline mass fraction in ISM can be 2.2%. But if you take a look in the evolved systems, say protoplanetary disk and the planetary systems, we see that the crystalline fraction of the dust is higher. We see in protoplanetary disk, we see up to 30% of the crystallinity. And in planetary systems, it can go up to 70% or so. So the question arises, when does this dust get crystallized? So as I told you, in ISM, dust is amorphous. In evolved system, dust is crystalline. So when does the dust is getting crystallized? So answer might be in protostellar phase. So it has been reported by Potier et al. In 2011. They observed a protostar called now named HOP 68. In the protostellar envelope, they reported high crystallinity. It was between 14 to 17%. But how do you make silicate crystalline? You have to anneal it about 1000 Kelvin. But these protostellar envelope, where they detected the high crystallinity, they are cold. Their temperature is around some few tens of Kelvin. But what this suggested is that the dust is getting annealed in the inner region of the protoplanetary disk, and then with the help of outflows, these crystalline dust are getting mixed to the outer regions. But another interesting thing is, the protostellar outflows are ubiquitous. And at this point, I would request, please do not take any photograph of the next slide because I'm not allowed to share it, but it is like one of the very latest image of protostellar system with JWST.
So the session is live and
It is live on YouTube.
Yeah.
Can you cut it? I mean, no? Okay, we'll see. So, so these are the outflows in protostellar systems. And these are ubiquitous. I mean, if you observe any protostar, you'll notice, you'll observe these outflows. So does that mean that if I'm measuring the silicate crystallinity of any protostar, will it be higher? So we did that. So to do that, what we did is we created a very simple model. We take a continuum source that is a central protostar, and we place a cold absorbing screen in front of it that is mimicking the protostellar envelope. We filled a combination of dust in that cold absorbing screen, and then we match. Then we try to see what is the contribution due to various dust species in the envelope. So these are the dust species that we used in this study, and these are the results. So on the right side, you see it is HOP68, the high crystallinity source that people have reported. While on the right side, there is another sample protostar. So you can see the difference. At 10 micron, the absorption feature is broad and smooth. And this study we have done for 100 protostars, and it is an ongoing study. So for 100 protostars, what we have found is mean silicate crystallinity is about 2.2%. It means that HOP68 is an outlier. So to summarize, silicate in ISM are predominantly amorphous, but in evolved system, protoplanetary disk and planetary systems, it is crystalline. And it seems with our study that crystallization is not happening in protostars in the protostellar phase. Hence the question, when and how does the silicate gets crystalline is still open. So, and as I was saying, it is an ongoing study. So we plan to do it for every protostar in the solar neighborhood. And further a study that can narrow down this question is with JWST. What JWST can give you is special resolution, and that can narrow down the crystalline silicate in the protostellar systems. So in the upcoming cycles, we plan to do that study with JWST. And to summarize, when and how silicates become crystalline in planetary systems from protostars to planets, it is still open. Thank you.
Thank you. We're well within the time limit. Okay. So is there any question for the speaker? Okay.
Nice talk. So this is not related to directly to your work, but I was wondering what is the scale of these jets from the
Scales you mean in
Earth?
Okay, in our parsecs, or they can like extend to few parsecs. I mean, 1 parsec, 2 parsec away. They are like very large. Even if you see a image of a protostar and an AGN, you can't distinguish between them. Like scale won't be similar, but like they are very similar.
So how what the brightest temperature could be for this?
Brightest
Temperature
of envelope you're asking?
Oh, no, the jet. Yes.
Oh, jet. They can go up to thousands of kelvins. So they generate shocks in the surrounding medium, and those shocks is basically, if you see this image, you see this bright spot that is due to the shock. So these can go up to a few thousands of kelvins.
Thank you.
Okay.
As you said, these are still open questions, but there will be the proposed explanation for that. So what are these?
Sorry?
Any proposed explanation for those for that questions, like
How they get crystalline?
Yeah.
So the parallel explanations are like various. So people have also said that these could be due to non-thermal reactions. What can happen is exothermal reactions can take place on grain surface, and that can give it a sufficient temperature that can heat the grain and make it crystalline. So these kind of, and another one is what I was telling you, that the dust gets crystalline in the inner edge of the disk and then transported outside in the outer regions. So these are two most competitive in the market now.
Thank you, Himanshu. We'll thank the people today. And the last talk of this session is by Nirvan Dabla. And I'll be talking about broadband X-ray studies of unique magnetic electricity variable. Vertical. Opposite side.
Hi everyone, I'm Anirban. So last talk for this meeting. So already very few people and who are staying here. Thanks for being present. Okay. Yeah.
The presentation.
Yes, it should start.
You already
No, I thought it will be done in between.
Okay. You take as much time as you want.
Yeah, but actually I will be very concise. I don't want to bore you much. So I will be talking about the two unique magnetic cataclysmic variables. So and their X-ray properties basically. So just for a very brief introduction for these cataclysmic variable stars. So they are these accreting binary systems where there is a primary white dwarf star which accretes the material from its companion secondary, which is generally a late type main sequence stars. So that this name cataclysmic stands for itself because early astronomers have also seen these stars in sky with the naked eye, and where they have gone like several thousand times with more luminosity. So those events are actually when this white dwarf starts accreting the material. So after reaching a certain stage, the outer envelope that will undergo some thermonuclear reaction and it will cause some outburst, which is known as nova eruption. So this part. So this has already been covered in the very first talk of our meeting by KP Singh. So I will not be talking about this part. I will be restricting myself only in this part when the white dwarf is accreting the material. So next slide. Yeah. So the primary white dwarf, so here it is, or in this picture, here it is. So it has a certain magnetic field, and depending on the strength of the magnetic field, we classify them as magnetic CVs or non-magnetic CVs. So the white dwarfs with the strongest of the magnetic field of the order of 10 to the power 7 to 10 to the power 8 Gauss. So their magnetic field is so strong that can actually extends up to the inner Lagrangian point of this binary system. So here this secondary is overflowing in rho flow, and the material directly starts getting accreted by the magnetic field lines, by channeling of the magnetic field lines, and it falls on the polar region of the white dwarf. This is for the polars with the strongest of the magnetic fields, and this picture is for the intermediate polars. They have a slightly lower magnetic field than the polars of the order of 10 to the power 5 to 10 to the power 7 Gauss. So what happens in this case, since the magnetic field is not that strong enough, that will allow some formation of some partial accretion disk. But at the final stage, again, the magnetic field will start dominating and disrupt the accretion disk, and it will start channeling the material via the magnetic field. So near the shock, so what happens is actually finally when the material starts following the magnetic field lines near the white dwarf surface, it is coming with supersonic velocities and it will produce a strong shock with the wide of atmosphere. And this shock region is the primary origin of the hard X-rays for these sources. So what happens will after that is that there will be a post-shock region where the material will gradually cool down via thermal Bremsstrahlung radiation. It will be seen in X-rays, so it will be a multi-temperature Bremsstrahlung emission. And also there will be some cyclotron emission due to the presence of the magnetic field. But those will be seen in optical wavelength. Okay. So, sorry. Okay. So this is a typical spectrum for these magnetic cataclysmic variables. So this is the part. So few kVs to few tens of kVs. There will be the Bremsstrahlung continuum, and also there will be some sort of black body emission, which will be very soft X-rays of the order of with the black body temperature of the order of few electron volts. This picture is from a typical polar type star, like a magnetic cataclysm variable, AMR. So, and you can see also this cartoon picture here. I present how the cyclotron emission also comes, but anyway, I will not go into that because that will be in optical. So these polars have an interesting property because they have a very strong magnetic field, and that magnetic field can extend till the inner Lagrangian point of the binary system. So this magnetic field of the white dwarf can get intertwined with the magnetic field of the secondary star itself, and that can cause some magnetic locking. So just a crude analogy with our Earth Moon tidal locking kind of system, so that the white dwarf will always have the same phase towards the secondary. So this is a typical, so this is called as synchronicity. So the spin period and the orbital period of the system is perfectly same. But there are few exceptions, very few exceptions. So basically these four stars and four systems and couple more have recently been included. So they show a slight difference between their spin period and the orbital period. Now, in case of intermediate polar, since they don't have this much of strong magnetic field, so this magnetic locking is not happening. So they can have a very different spin period and the orbital period, a difference of the order of 90%. But there are again two peculiar intermediate polars, Paloma and this V697 score, which shows a very smaller asynchronicity compared to the intermediate polar class, so of the order of 14%, 24%. So what we did, we tried to look into two unique objects of this kind, so which do not perfectly belong to either of the polars or the intermediate polar class. Rather, they are called kind of asynchronous polar systems. And we have tried to look into these objects, try to study their properties in broadband X-rays. So for that, we proposed an joint observation from XMM Newton and New Star Observatory. The observation was carried on last year. So we obtained the data and we have analyzed the data and tried. I will just briefly discuss about the results that I have found. So this was a strictly simultaneous observation. I mean, so they're overlapping. So on the same date, the observation started by both these extra observatories, ranging from 0.3 keV to 78 keV. So the new star exposure time was around 56 kiloseconds. So you will get a overall of around 90 to 100 kiloseconds of observation duration, considering the Earth occultation by the satellite. And XM Newton has a continuous continuous observation. So it was of the order of around 36 kiloseconds, but we had to reject some part of the data due to background flaring and so on. So this is the CD as seen by New Star, and this is as seen by XM Newton. Okay. So for the timing studies, I'll just briefly discuss what we have found. So in the literature, the spin period and the orbital period have been measured by Littlefield et al. Using 1 month long optical TACE light curve.
And they have found a very precise measurement of the spin period and orbital period of the 6648 and 6720 seconds. These are very close by. So we have used their found period values. So we have folded the total light curve on the basis of the spin period, and we have got the spin folded light curves. So basically 0 to 1 means one spin cycle of the white dwarf star. And we have obtained the energy resolved light curves in 0.3 to 3 kV and 3 to 10 kV from XMM, and 3 to 10 and 10 to 40 in Newstar. So if we look into this first panel, so it gives a very a broad hump-like feature. We look like this. So which is kind of consistent with a single pole accretion model, which is already existing in literature from other wavelength data. And so people have considered that there is some pole switching is happening for this kind of object. So at any point of time, at any point of the bit phase, bit period between the spin and the orbital period, any one of the pole, either the north pole or the south pole, let's say like north and upper or lower pole of the white dwarf is actually accreting. So this broad hump is one broad hump during one phase, total complete spin phase is actually representative of that. But there are several narrow dips. So these narrow dips are coming from very strong absorbing, like inhomogeneous absorber, which is possibly contributed from the accretion stream near the white dwarf. So this is the light curve in 0.3 to 3 kV. But when we look into 3 to 10 kV, we do not see this kind of broad hump-like feature like that, but the narrow dips are still present. So what we hypothesized here is that maybe the very so these soft X-rays 0.3 to 3 kV are mainly coming from the very bottom part of the post-shock region or near the white dwarf surface. So that is getting self-occulted, or that is getting mostly modulated over a spin cycle, whereas 3 to 10 kV, which is coming from much above the white dwarf surface, this part is always remain visible to the observer. So it is not getting modulated as such by the over a spin cycle. So the same pattern we have also seen when we looked into the Newstar light curve. So basically more or less a flat light curve, but with some fluctuations in between. So as well as the 10 to 40. So it basically represents some kind of very tall shock scenario where the very hard X-rays, which is near the shock region of the of this post-shock region, which is at a certain height, and that height is a considerable amount of height. So those X-rays are actually not getting that much modulated as the soft X-rays, which is coming from the bottom part of the near the white dwarf surface. And we have also seen there is a very strong variation in the hardness ratio when you compare the medium to soft X-rays. And this part, when we have looked into the X-ray spectrum here, so you have seen that below 3 kV, we see so around 0.7 to 1.5 spin phase. If we extract the spectrum only for that part, we have seen that there is the flux is very less compared to the rest of the spin cycle below 3 kV. So this actually supports our assumption that there is a very strong absorption which is happening during this region. So that is why it is causing this spectral variability. And so this is that. And also we have found that so the amount of the absorption that is increased by this time is around 8 times. Also from the broadband fitting of this data, we have found that the shock temperature is around 43 kV for this system. Now this shock temperature is representative of what is the gravitational potential of these white dwarfs. So basically more massive the star, more will be the gravitational potential, higher will be this supersonic, higher will be the shock temperature. So we got a white dwarf mass of 0.87 for this system. And also when we looked into the grating data from XM Newton, that is the RGS detector, we found there is a strong spectral emission from oxygen ionized K alpha lines. So these actually indicates that there is some extra optically thin emission is happening from the bottom of the post-shock region.
You crossed 30 minutes.
Oh, I'm not concise. Sorry. So, okay. So just one more brief concept that we tried to prove here is that in several IPs like D1223 SGR, B709 CAS, people have found that in X-rays that so there is a Compton hump which is present from 10 to 30 keV, this hump. So these happens when like hard X-rays, which is coming from the shock front, which gets reflected on the white dwarf surface. Let's take this as a white dwarf surface and gets re-emitted as a Compton hump here. So basically inverse Compton and some Compton upscattering both happening, and which increases the hump like, which produces the hump like feature around this energy range. But when we looked into our source like CD-IND, we did not find any such feature around 10 to 30 keV. So actually this, if there is a strong hump-like feature, then actually it indicates that the shock is happening more closer to the surface. So this also supports our scenario that the shock front is tall. So there was another source, another unique source that we studied. The similar kind of studies we performed on this from Newstar and XMM Newton. So this is for Paloma. And here I will just show that we got the power spectrum and we tried to measure the, our observation window actually enabled us to measure the spin period and the orbital period precisely for this case. But one interesting thing that we have found is that the orbital period is, orbital frequency peak is very strong in the power spectrum. Whereas the spin frequency peak is not that strong, and also the spin modulation, of course, is not that strong. So it was a kind of a distinguishing feature for this particular source, because generally in kind of IPs, there is a like the spin frequency peak is at least as strong as comparable to orbital frequency peak, or more than that when seen in X-rays. So so that's why we have actually folded the light curve based on the orbital period. Just the key takeaway from here is that we have also seen several dips here and one broad hump-like feature. So since this is an orbital orbit folded light curve, so basically these peaks which are coming in both in all the energy bands. So similar kind of study as like the earlier. So this is the this is kind of happening there. Probably there may be some dense blob-like material which is producing this strong orbital variation. Whereas these smaller peaks or this peak here, particularly in the soft X-rays, these are coming from a very strong absorber. So the spectral study actually supported these assumptions from our timing studies. And in this case also, we have tried to measure the shock temperature and try to get an estimate of the white dwarf mass, which comes around 0.74 solar mass. And also in this case also, we didn't find any significant reflection hump here. So basically in this case also, we assume that the tall shocks scenario. And yeah, so this is the summary for these two. So these shows similar kind of spectral properties and timing properties. And we plan to extend our studies for other asynchronous polars, whether they have like any other similarities with whatever we have found from CD-IND and Paloma. That's all.
Okay, thank you, everyone. Any question for us? Yeah.
Hi, nice talk. Can you go to the slide related to the timing analysis
for
CD first? Okay. Yeah, so here you have written the single pole accretions.
Yes. Basically, they are considering this pole switching. So the bit period for this system is of the order of, I think, 7 days. So this Newstar and XMM observation only extended for like 1 day. So XMM had a smaller observation and Newstar has a longer observation. So it extended for roughly 1 day. So during that part of the bit period, only one of the pole was accreting. So if you look in, if we had the data from other part of the bit phase, there will be another pole which will be accreting.
You need like longer data.
Yes, but getting a 7-day long data from Newstar and XMM Newton, they won't accept that proposal.
Thank you.
Yeah.
Spectrum, XMM Newton.
Okay. We did a joint, broadband spectral study. So we tried both the Meckel as well as MKC flow. So multi-component Meckel was there as well as MKC flow was there. Even with MKC flow, we needed one extra Meckel component for the soft X-ray part from which is coming from the X-ray. Yeah.
Spectrum, can you go to your spectrum?
Uh,
CD you have shown there.
yes.
The starting slides.
This one?
The complete SAD you have shown of the sources in the starting slides.
Okay. Okay.
Okay.
So that data point is of in which range? The first data point which is about.
So this is okay. It's this is 10 to the power minus 3 kV. And this is 10 square kV, so 100 kV.
The first data point which is at the top, if we can see.
This one?
That.
Oh, okay. So this is actually if there was no absorption present for this AMR, then this would be the spectrum. But because there is some absorption present, if we consider all the galactic absorption as well as the intrinsic absorption, this is actually the real spectrum that was seen. So
that is not observational data.
No.
So,
Yeah. I have a naive question.
Yeah, sure.
Is there any transitional event between the intermediate polars and the polars?
Yes. So there are certain hypotheses where people try to put forward this idea that intermediate polars will finally translate towards being a polar. But like these are all hypotheses, and these are not been like a very conclusive
Because
thing.
the magnetic field can be enhanced.
Yes.
Because during this accretion process also
Yes.
the magnetic field can be enhanced.
Yes. So this is one of the ideas. So that it was one of our motivation to study these kind of objects.
Thank you. I'm going for the next thought. This concludes the final contributory talk session, and now we'll break for tea and gather once again at 3:45 for the final and concluding remarks. Okay. So we can break for tea now. Tea and
Yes.
We can.
Yeah. Our question.
দুটো comparable এটা কি X-ray binary ক্ষেত্রে
সেই লগ আইডল লগ নয় আইডল লগ মানে ইয়ে আইডল কোর্সের জন্য যত বেশি আমি বাইনারিতে যে স্কিলে বুঝছি আটকে রয়েছি এই প্লেনটা হচ্ছে অরবিটাল সোর্সের সাথে ওর স্পিড ওয়াইড কন্ডিশন
Can you please ask the question? जो मास फंक्शन कर बोलो
फाइनली नेचुरल तो थोड़ा लाइटली भी होता है, मतलब ऐसा नहीं रहेगा कि ये छूट गया वो छूट गया, अभी इंटरवल वाली स्लाइड चली हुई हाँ वो उसकी
बैठ के बात करना साथ में दिखाता है, साथ में अच्छा अच्छा
बिना माइक के भी जाएंगे और हाँ,
ये क्या कर दिया आपने?
कोई बात
कोई नहीं, एक ही में हो
Okay. Okay, good afternoon, all of you. Now, after 4 days, it's time to conclude our event. So, YAM 2022. So, let me start with the statistics of YAM, where it started. So, it started with the registration of the interesting, okay, statistics of YAM. So, yeah, okay, I'm sorry. Let me, okay. So you can see the registered participant, we got the registration from different affiliations, different institutes. So you can see the map, and after after looking at this map, what was the condition of the LOC member? You can see here. So they were confused how to select 50 out of these 300. 308. 308. There were 308 abstract we got, and then they found that how we were expecting actually 150, and the auditorium space itself has capacity of 90. So we were in a mood like there will be 150 participant abstract, and we will select 90 out of them, and maybe all of them rest in e-posters. So now they, yeah. And finally we selected 160 and 83 e-posters, 52 for talks and 24 for posters. And the distribution of these, the contribution type is poster. We selected 24 poster, 52 talks, 83 e-posters with affiliation 30% from universities, 21% from areas because of the accommodation problem again, because areas are accommodating, areas people are here only. So they are automatically selected. So I'm 56 from outside. There were 6 categories of presentation from different categories. So we took the ratio same as the ratio of the selected extract is same as we got for the registered participants. So this is the gender. 39% are females and 60% are male. Now this is distribution of states. You can see that most of are coming from the Karnataka, and it is obvious because Bangalore is the hub of astronomy. So this is distribution over the map. Thanks, Arpit. And and now our auditorium was ready by 8th of November, by the night of 8th of November, thanks to volunteers, all LOC members for all these efforts.
So night before the start.
Night before this one, 8th of November night. Now glimpses of program. So it started with the inauguration by director, and then we have invited speakers, different invited speakers. You have heard, and then outreach activities by the invited speakers. And this is the first day. This is the first day. Arpit has played multiple roles. He was photographer too. So first day it was the excitement to see the sunset, and now the last day they will see from the Hanumangadi, maybe from the Nainital. This is a hands-on session at 14-inch telescope, and thanks to Atharva. So
This guy reached on 9th itself at 2 o'clock in the morning. Okay. And at 9, at 11:21, he was teaching us these demos, how to present. So this enthusiasm we need for outreach activities. So thanks, Atharva. Without you, it might not be possible to do outreach activities at the school. Thank you. And this is 11:30 p.m. day 2. We all LOC members were there doing the preparing the material for outreach activities. And this is mandatory. Efforts by Shura. This was his 12 a.m. Okay. This is Gaurav Energy. Okay. Next, these are school students. Artists again in different roles. Thank you, Vishal, for this beautiful picture at the school. And then Bhavya Prajal. And you can see the sunspot, maybe. Is it visible to? Okay, there are sunspots. Within the other doing the, and then it's time to thank you all guys. A vote of thanks to ASIP OEP, to Director of AREEF for providing guidance and engagement with the YAM organizers. Please. Then to invited speakers who give precious time and share their experiences. And the canteen staff had this delicious food for 4 days with the mutton biryani. You might remember. This guy, the bus driver. Thanks to SOC members. Evaluate 308 mistakes. That was really a tough
When we were
job.
registering for the conference, so we were expecting 150 abstracts. So we asked all of them, we will give you 15 abstracts each. And now when the registration came, they were given 35. Vishal, how many were there? 41. He were 41. So this was the kind of workload that these guys had.
Thank you. To LOC members, to volunteers, can you right. अब
बहुत फास्ट मूव कर रहे हैं
इनके लिए भी थोड़ा क्लैप हो जाए volunteers ने बहुत काम किया है and then of course the participants here contributors and then the final glimpse of the program.
तो लगा नहीं तू ऊपर लगा दे क्या
This is edited. पहले ऊपर ही लगा था हवा की वजह से वो 2 दिन पहले उठ गया था फिर उसको अंदर लगाया गया था अभी डिजिटली लगा दिया है वो प्लान था एक्चुअली उसका
So
and tomorrow we will all go to Devastar and we have culture night today at 6:30 so be present there and जितने भी कलाकार लोग हैं आपको अपनी कला दिखाने का पूरा मौका दिया जाएगा उधर यहीं पे होगा कल्चर आपको 6:30 we are expecting.
So this
You want to say something?
So in the schedule, basically, we had a discussion session scheduled after this. So now looking at the audience, I mean, a lot of people have left already have left for town. So if you guys are interested, we can have a discussion session right now, or otherwise we can maybe shift it at a later stage. Maybe we can. So if you guys are really interested, then we can have some discussion on going on. I mean, about the pros and cons of this event, or I mean, if you have any suggestions, if you have anything to add to it, or something like that. Or any comments?
feedback जरूरी है ना
Feedback के लिए हम आपको will form make a Google form and send it to you. This you can do even after YAM. वो memories नहीं जाएगा ना एक हफ्ते के वीडियो भेज देंगे. So I hope you remember. And so if you have any quick comments, anyone, so you can.
Just one comment. There should be a bus after 5:20, please.
There will be.
So I mentioned that to you regarding
Yeah, I mentioned you about this group two for connectivity. If you can say something about that.
Yeah, so Rashid is talking about, so basically what he said that when we disperse from here, so maybe we will not be in touch with each other after a long time. So he suggested we should make a WhatsApp group or some sort of something like that. We're always connected on WhatsApp, so maybe we all can join that group and we can be connected to each other.
We
That
have
is-
Slack, right? Slack is there.
We have Slack, but the problem with Slack is that after 90 days, messages are gone. So it's only for 90 days. So until 3 months, it's okay. After that, it doesn't matter much. So this is why he suggested that maybe we can form a WhatsApp group and stay in touch with each other.
Also, like WhatsApp is a go-to place and people will be more active.
So that we can do. So maybe Slack is active until 90 days. So we'll form a WhatsApp group, send a link on Slack. Maybe you all can join who are interested. And then we can continue with talking with each other. Right. Yeah. So anything else? Okay.
Including us.
Everyone just want to leave and then. So
I had one suggestion regarding this poster session. So if like it could have been distributed in like multiple days with like few people will be given like posters before and then in next session maybe some others were allowed to present. So maybe like 8 posters in one day and then in next day 8 posters. So it could have been like more discussion friendly. Otherwise, like if you had sessions, so most of the people discussed at that time only and afterwards it was kind of empty. So like
physical poster.
physical poster. But like session wise, like suppose you had some kind of talks, the posters related to that could be displayed. And maybe after 1 or 2 days, others could present like posters related to the talks. That kind of thing.
That is a good idea. Yeah. So we were thinking that we'll just display the posters and during tea and coffee breaks, maybe we can have chat about that. But yeah, it can be scheduled that way, so it will be more efficient.
You should have more break times.
Yeah.
That's the place where discussions happen, right? So yeah, so some more spacing between the breaks, but I think you can't help it.
I mean, we had a very tightly packed schedule. 52 talks, I mean, it's very difficult to organize. And then we had all these activities also. So
I didn't see anybody's posters, that's why. I saw some posters only today. You can see it now, we have 1 hour. Yeah, that's the other thing, right? I mean, yeah,
I understand. It could have been.
yeah, huge round of applause to these two people for getting so much getting it done. They're always available on WhatsApp, on call, at any point of the day. And they were, even if they were zombies, they were coming and helping us out in outreach and coming here and whatnot. So yeah, thank you both of you.
Thank you. So now, I don't know, anyone was there in last year, 2019, on the final day? Okay, so I'm not sure about it, but there was a culture that, I mean, you nominate your institute on the last day of the and maybe your application is forwarded to the sponsor, and then they basically, I mean, allot who is going for the next year. I don't know how it works because now it is supported by ASI. So what we suggest to you, so how many affiliations do we have? Aries people, can you raise them? Yes, mostly are Aries only. We can see people from ISC, Ayuka, and someone from TFR. You are from TFR, right? Okay. So maybe then it's not a good time to discuss about it, but see, when you have to organize the next edition of PM, so basically now you have to write a proposal and then your proposal will be forwarded by ASI, I think. So ASI will then allot because if you receive multiple proposals, so we request all of you, I mean, not people other than Aries, that you submit proposals and maybe host PM next year at your institutes. And we'll be very happy to help you with all these things. And we'll be sharing all the results that we obtained. We have some detailed results also. We're sharing all these results with ASI and maybe they can all communicate it with you. So that, I mean, you can plan it further, the thing we have missed, shortcomings, so you all can take into account. Right. So this is it from us then. It was a very nice meeting you all. And we hope that you had an enjoyable time here for the past 4 days. And so let's clap for yourselves. Yeah. So today we have a cultural evening at 6:30. So Dimple will be taking care of that as she has been taking care of so many things. So 6:30, I think we'll gather here. And those of you who are interested in participating, singing, dancing, anything, you can just present yourself. Non-academic things, everything is welcome. Okay. And tomorrow morning we have a visit to Devastal. So we'll be leaving at around 10. So you finish breakfast by 9:30. We'll just gather around near the guest house. So at 10 we'll leave. And tomorrow your lunch will be served there in Devastha Reserve, and by evening we'll return. Okay. So yeah, so by evening we'll return here, and those people who are leaving for Haldwani tomorrow itself, so we have arranged a vehicle for you. So from Devastha Reserve, you can go to Haldwani. Right. So yeah, those people who are leaving tomorrow evening from Haldwani, you can pack your luggage and put in the bus itself. Then maybe it will be easier for you. And you don't need to come back to it. Okay, so that's it from our side then. See you in ASI waiting.
जो कप मैंने लेके जाएगा नहीं मैं लाया हूँ